supposed to continue with our analog CMOS design, but due to some unavoidable circumstances, Jatana ji has to leave the station and he is not available with us. So that is why I am going to continue with this session. And in this session, we are going to discuss VLSI design flow. Right. So in VLSI design flow, outline of this program are this session are first of all we are going to discuss the overview, then design flow, then we are going to discuss front end VLSI design, back end VLSI design, then conclusion and references. First of all, overview. As we all know that there are basically three domains in which we can work. And those three domains are behavioral domain, structural domain, and physical domain. So depending upon the input with the designer can work in any one of these three domains. For example, if you want to work in behavioral domain, then designer has to design his system based on some code, and that code can be your VHDL code, Verilog code. So basically this domain deals with programs in the form of softwares. You can enter your program using VHDL or Verilog. Then you can use sub programs in that, subroutines, and then instructions. So basically behavioral domain, in behavioral domain you explain the behavior of your complete system. Next is your structural domain. In structural domain we start our design with schematic. It can be in the form of transistors, it can be in the form of gates, registers, and from gates and registers we can go ahead with processors. So basically structural domain is in the form of you can say a schematic diagram. We can use transistors, gates, processors, and then we can design our system by using these different you can say architectures. And the third domain is basically physical domain. In physical domain, this physical domain is mostly linked with your backend VLSI design, whereas we can divide our VLSI design in two parts. One is front end and second one is your backend. In front end design, we can work in both domains. Behavioral can support your front end, and then structural can also support your front end. Whereas whenever you have to work on backend VLSI design, then we have to choose this physical domain. In this physical domain, basically again you design your circuit. You design your circuit by using different modules, different gates. Then you can have processors also, and you have to go up to the physical level where you get the mask of different layers, you can say. So working in all these three domains, it depends upon the you can say software available with the designer. It depends upon the input with the designer, whatever input is there with you. So based on the software and different inputs with the designer, you can opt for any one of these three domains. And no doubt software plays very important role. If you want to work in any one of these software, then we should have in these domains, then we should have that supporting software also with you, so that you can work in that particular domain. Now whenever you go for any kind of VLSI design, the important parameters that normally we consider from our design point of view, and some of them are first of all performance, and you check your performance of your design based on speed, power, functionality of your design, and how much flexibility is there in your design. So these are different performance parameters that a designer can consider in VLSI design. Then also another parameter is size of your area or size of die, so that you can keep the cost of your design very minimum. And third parameter is very important parameter, that is your time to market parameter. Whenever you go for any kind of design, you should be able to complete that design within small time period, so that you can launch your design in the market. otherwise, if you really want to compete in the market, then you have to complete with your design in a very small time, and you should meet all the specifications, desired specifications, and you have to be competitive in the market. So this parameter is very important parameter, so you have to take care of this time to market factor also. Then in our VLSI design, two possible combinations are there. First one is you can go ahead with ASIC design. For ASIC design, basically ASIC stands for your application specific integrated circuits. For ASIC design, different softwares are available in the market, and depending upon the software with you, you can go ahead with your design, and each and every software differ in performance. They support different number of parameters, and depending upon that you can design your circuit. So some of these softwares are Cadence provide Virtuoso software, then Synopsys software is there, Mentor Graphic also provide a good solution for VLSI design. Then we have some lower end softwares. These first three softwares are basically, you can say that these are industry standard softwares, and Cadence Virtuoso is extensively used. Synopsys is also very much used in our educational institutes as well as in industries. Mentor Graphic is also providing very good support for VLSI design. Apart from these softwares, some lower end softwares are also available in the market, and those softwares are low in cost, but from understanding point of view, these softwares can also be used to understand the flow of our complete VLSI design. And some of these softwares are Microwind, Tanner software is there, so you can use these softwares also for your VLSI design exposure. And if you basically ASIC design, we talk about this backend VLSI design. When we go for programmable integrated circuits means you have some programmable chip in your hand, and then you have to program that chip with the help of some programming language, and that programming language can be your VHDL, Verilog, and some vendors they are also supporting C language. Under these programmable integrated circuits, we have options. You can have SPLDs, simple programmable logic devices, CPLDs are there, complex programmable logic devices, then you have FPGAs, field programmable logic devices. So these are different hardware platforms, and Xilinx provide these platforms. For example, FPGAs. In FPGAs, you can have Spartan-based FPGAs. You can have these Vertex-based FPGAs provided by Xilinx, and then Altera also providing a very good range of FPGAs. So depending upon the FPGA you have, you can opt for software, and then you can program that particular FPGA for your front-end VLSI design. So these two main options are there. Depending upon these two main options, we can go ahead with our design part. So these also act as input to the designer. Whenever you start with any design, first of all you should know what software is there with you to design this particular system. Whether with that software can work in front end or that can work in back end. So all those kind of inputs should be there with the designer, then only you can go ahead with your next part of your designing steps. And if we go for complete design flow, apart from these this knowledge of softwares and knowledge of available tools with the designers, you should have complete knowledge of first of all specifications. So what specifications are there with the designer? System specifications. If you are making any design using let us say you are making any VLSI design, you are making SRAM, then for making that SRAM you should have knowledge about on which technology you are going to work, whether you are going to work on 65 nm technology or 45 nm technology. Right, what are your design constraints in terms of speed, how much speed is required from your design, then how much area you can consume for that particular design, and power consumption also. So these are some design constraints that you consider while you go for your design. And all these are basically constraints, and these are the category under which you are going to give these system specifications. And if you go for a larger system design, like for DSPs, or you can say any embedded system design, for example, in DSP, if you are working for you are going to design some filter, then you should have specification of that filter, specification in terms of means different parameters of those filter. So these are some design specifications that you should have before starting your design. Once your design specifications are complete, then based on these design specifications, you go ahead with your code development. And that code development can be in your MATLAB environment. You can write your code in MATLAB. And then once your code is developed in MATLAB, then you go for its simulation in MATLAB itself first. Then once your code is developed in MATLAB and simulation is as per your design specifications, then next step is you have to now move towards the hardware platform. And MATLAB gives you the required input for hardware implementation, and that input is let us say we are making one digital filter. In digital filter, MATLAB is going to give you the order of the filter, and it will give you the different coefficients and their coefficient values, and those coefficient values you can use further in your hardware implementation part. So by taking this input from MATLAB, we can move on to its implementation on FPGA, field programmable gate arrays. And that implementation can be either using VHDL or Verilog. Once your design is implemented on FPGA, then you synthesize your design, and you check the parameters, you check the area consumption of your design, you check the speed of your design, you check the power consumption. So those things comes under this category of synthesis. So once your simulation and synthesis part is complete, next thing is your placement and routing, PAR. In placement and routing, you place your circuit on prefabricated resources, and actually FPGA contain prefabricated resources. Whenever you go for ASIC design also, you can have some prefabricated resources in terms of soft IP cores or hard IP cores. So you can use those IP cores in your design, or you can go ahead with the complete custom design, where you have to create each and everything at your own. So in that case, you will not get any prefabricated resource on your platform, but in other options you will have prefabricated resources, and you have to place your design on those prefabricated resources, and then you have to make connections between those designs, and that part comes under the category of your routing. And once your placement and routing is complete, then the next step is your implementation part. Implementation part is now you are going to design your complete your design in hardware. Your design is transferred to the hardware part, and now you have to check the functionality of your hardware. So there you check the whether your design is working as per your specifications or not, and this design is basically this checking is on your hardware part only. So as I told you, we start with our design specifications. If you are going for a filter design, and those design specifications, your can be your first is your this it can be cutoff frequency, pass band frequency, stop band frequency, pass band ripples, filter order. So you can start with these different specifications. These specifications are there with you. Once these are there, then you can design your filter in MATLAB, and you can simulate your filter, and MATLAB is going to give you the value of each and every coefficient, and then you have to convert that value into digital form. Other important performance parameters here are how much area your design can consume, this one, second, and then your speed, what should be the speed of your design. And you have to take care of all these things. Once you give or you design your system by using these above specifications. Now you have to take care, you have to optimize your design in terms of area, in terms of speed, and in terms of powers also, if your design is basically used for portable systems. So your area and speed, it depends, completely depends upon your filter order. So whenever you are going to design your system or your filter in MATLAB, you have to take care of this parameter. You have to keep this filter order minimum possible, right? So after this complete optimization in MATLAB, next thing is your code development in hardware. And as I told you, this code development can be in MATLAB or it can be in ISE. Whenever you are working in MATLAB, you are going to write M code for your filter design. You have to specify all the design specifications in your M code, then you have to simulate it. From there you will get the coefficient values, exact values, and those coefficient values will be used in your HDL code. And this code can be either your VHDL code, as it is mentioned here. This HDL can be your either VHDL or it can be either Verilog. Next thing is whether you want to make your design serial architecture. You want to choose whether you want to choose serial architecture, you want to choose parallel or partially serial. Actually again there is you can say compromise between speed and area. If you go for serial architecture, then it will be area efficient, cost effective, but its speed will be degraded, or we have to compromise on speed part. If we go for fully parallel design, then in that case your design will be costly because you are going to consume more resources, but your speed will be more as compared to your serial design. If you want to optimize between area and speed, then another option is there, that is your partially serial design. In partially serial design, we optimize our design so that we can get means optimal. We are going to consume optimal area by giving the required speed. So this is in between solution, partially serial architecture, in between solution between your serial and parallel architecture. So depending upon the requirement, because these are the inputs with the designer, and designer consider these inputs, and by considering these inputs, designer can select either serial, parallel, or partially serial architecture. So once your VHDL or Verilog code is complete, then you check its functionality. You check its functionality by using now different simulations are there, different simulators are available in ISE environment. For front-end VLSI design, you have ISE simulator. Apart from ISE simulator, you also have model sim simulator that can also be used to check the functionality of your circuit. So once the functionality is as per the required specifications, or it is as per your design specification, then the next step is synthesis. So in this synthesis part, three main things are considered. This synthesis gives you the consumption of resources in your design, and it also gives you the speed of your complete design, whatever speed you are going to get from your design, and also you will get power consumption of your complete design. So once your simulation is complete, synthesis is very important parameter, and mostly we calculate resources, speed, and this power consumption in our designs. And whenever you are going to search for papers, IEEE papers, or any other good journal papers, you will see that those papers are basically based on either functionality. First of all, your design should function as per your requirement, and then you will get its resource consumption of your circuit, and then speed and power. So you will get papers based on either one or more than one parameters, like it can be speed and area, it can be your area and power, it can be speed. So different kind of papers you will get on different journal sites, very good journal sites. So after this one, the next part is your placement and routing. Placement, basically, once your circuit is complete, your system is complete, then you have to place that circuit either on your silicon area. And if you place your circuit on silicon area, then it means that we are talking about ASICs and we are working on back-end VLSI design. Or you can place your circuit on existing resources, and those existing resources can be your CLBs, PLBs in case of your PLDs and FPGAs. So placement is very important parameter in overall VLSI design, because once your placement is optimal or correct, you can say that, only then you will be able to route your circuit 100%. So routing of your circuit depends upon the placement, and optimal routing depends upon the placement. So we can say that this placement and routing is not, these are not basically two separate things. These two things work together. When we place, then we route the circuit, and we check the all parameters, its speed, its power consumption, and then if it is not as per our requirement, and if it is not in our required limit, then you have to again change the placement, and again you have to route the circuit. So routing is basically again it depends upon placement, and you have to find out the optimal path between your placed resources. Efficient placement and routing is very important to achieve you can say this high speed and to reduce the area consumption of your design and power. Basically all these three parameters, important parameters, are linked with your placement and routing. So, and the last part is your implementation. Once your circuit is placed on either silicon area or it is placed on your prefabricated resources, then you have to check your circuit on hardware platform. So in case of front-end VLSI design, we can use SPLD, CPLD, FPGA to check our complete system. And in case of back-end VLSI design, you have to make your chip, that is ASIC, and then you have to check the functionality of your ASIC. So these different options are available with you. So first of all, we are going to start with our front-end VLSI design. In front-end VLSI design, we have three options. First one is your HDL development. Second one, you can use CoreGen, and third one is DSP tools. In three options, first of all, you should be very clear for what kind of option you are going to go ahead. So first is your HDL development. If you want to go for HDL development kind of option, in this case basically you should have good knowledge of your HDL language. You should be comfortable with VHDL environment or Verilog environment. Once you are comfortable with these two languages, with or any one of these two languages, then you can write your own code either in VHDL or Verilog by taking the desired inputs, and then you will go ahead with your design. So if you you want to work in HDL development flow, you should have good knowledge of your VHDL or Verilog. So once this VHDL or Verilog code is complete, then next part is again your synthesis. In this part, it gives basically information to the designer about the required resources along with net list. Means how these resources are connected with different nets, and finally once your all resources are connected with each other, then you check its functionality. So you check the functionality of your design. Then next part is implementation. In implementation here we have three things. One is translation, second is placement, and third one is your routing. Translation basically is the binding of your resources. Let us say your design is complete, you have one RTL with you, that is register transfer level logic. So you have to now map your complete design with available resources in the software library. So you have to map it efficiently, and that part comes under the category of your synthesis, and that kind of synthesis is known as your technology dependent synthesis. So basically you map your complete circuit by using different resources of existing library, and you try to optimize your design, and that comes under the category of your translation. Once all the required components are selected from the library, then next part is where to place all those components on your either silicon area or on the available resources on your FPGA. So once again, this is very important part. You have to place your circuit very efficiently, so that your circuit takes very less area, and your circuit should be routable. If you can't route your circuit, then you can't complete your design. So two important parameters are there. You have to place your circuit in such a way that the area of your system is very less, and your circuit should be routable. So we then different second thing is routing, and again you have to find out the shortest path, or you can say critical path, and that path is going to give you the minimum delay in your complete design. So in front-end VLSI design, once these three steps are complete, translation, placement and routing, next step is your after these steps a file is generated that is known as your bit file. So you will get one bit file in terms of zeros and ones. So now your next step is you have to transfer this file that is in the form of zeros and ones from your PC to your FPGA platform. So once this file is transferred from your PC to FPGA, and then you are ready with your hardware verification, in circuit verification. You can now check the functionality of your circuit on FPGA. You can give different inputs. You can by giving those inputs you can check the functionality of your complete design. And second option is ISC core gen. In ISC core gen, basically if you are not aware, means very much comfortable with either VHDL or Verilog, then ISC environment also gives you option of core gen. Some IP cores are already available in your ISC environment, and you can use those IP cores in your design. You can select those IP cores, you can use those IP core in your complete system design, and ISC is going to generate HDL, it can be VHDL or Verilog, based on those IP cores. And once your VHDL is complete, so it means that HDL part is now it is you can skip that part, and you can generate your VHDL or Verilog from core gen, and rest of the steps will remain same. Means your VHDL is complete. Now you have to synthesize your design. After synthesis, again you have to implement again, consists of your translation, placement and routing part. And after this one, again bit file will be generated, and you have to download that bit file to the FPGA so that you can again check the functionality. So ISC core gen is also very important. It plays very important role where IP cores are available. So these are some different IP cores. You can see that you can use these IP cores for generating your VHDL. Here you can see that some options are there for FIR filters also. FIR filter is there, then RS codec, then a turbo coder is also there, Viterbi coder for communication. So these are different FFT you can calculate. So these are different, you can say, IP cores available in ISC core gen. So you can use these IP cores, and straight away you can generate code for your VHDL or Verilog. So this is one option for generating VHDL or Verilog. And if you look into this complete flow now this complete flow, basically you start with what? You start with this part, you write your code in VHDL or Verilog. So once your code is ready, then you go for synthesis, and after synthesis you get netlist, and that netlist means here you get the all the components used in your design and their connectivity with each other, that comes after this synthesis part. Then next thing is your mapping. This mapping is again your translation part, mapping, placing and routing. So once your netlist is ready with you, then we perform these three steps: mapping, placing and routing. And after performing these three steps, you get one bit file, this bit stream. That bit stream will be in the form of what? Zeros and ones. And once you get this bit stream, then your last step is you have to transform this or transfer this bit file onto the FPGA. Here this is your FPGA Spartan 3E board. So you download this bit file on FPGA and then you can check the functionality of your complete design. So this is the complete design flow from starting from your VHDL or Verilog. Then here you can see that this is the closer view, or you can say the zoomed view. This is Spartan 3 FPGA, and these are some input switches. You can provide input from these switches, and these are some outputs you can use in your design. So by using FPGA you can easily implement your design in hardware. These are some inputs and these are some outputs. Depending upon the functionality you can check the input and output. Next is your third part is DSP tools. So in this one in DSP tools we have different options. Basically these tools are used to bridge the gap between your MATLAB. This is your MATLAB environment and this is your ISC environment. This is ISC environment and this is your MATLAB environment, and there is a gap between these two environments. You once you get different values of coefficients, and if you want to implement those things with the help of ISC, you have to first of all convert each and every coefficient into its equivalent 0 and 1 value, or you can say you have to generate you have to convert that floating point into fixed point by in the form of zeros and ones. So this gap is basically filled by using ISC DSP tools. In ISC DSP tools, again you have you work in this MATLAB environment, and from MATLAB environment again you can generate what? VHDL. VHDL will be automatically generated by your this MATLAB environment, this one, and again you can skip that development part of your HDL. So whenever you are going to design any kind of system, let us say you want to make any communication system, you want to design filters, you can start with MATLAB. You can generate VHDL or Verilog, and rest of the steps will again remain same. You have to synthesize it, then you have to implement and download. So again you have one option of DSP tools. In DSP tools again you have two options. One is your system generator and another one is your Excel DSP. So when we use this system generator, as we all know that in this MATLAB, either you can work in MATLAB environment by developing M code, or you can work in a Simulink environment where you can design your system by using blocks. So whenever you are using in Simulink environment, then you have to select, you have to work in system generator, and this system generator is used to bridge the gap between your this MATLAB environment and ISC environment. So whenever we work in Simulink, you can select different uh, blocks from different libraries. Like you have different libraries, Simulink library block set. This is for math. Function is there, sinks are there, sources are there, and then one library is there for DSP block set. You can select from there filters, transforms. Another block set is there related to communication like modulation, DPCM, and by using these block sets from Simulink environment, we can combine these block sets with system generator environment, and then we can come up with one complete system design, and that system design can work as hardware implementation. So it can be easily verified on your screen or hardware platform. So likewise, you can see that here we are making our design using these different blocks, and then you are checking the simulation part here. So this is the design flow using your Simulink and system generator. Next is your XLDSP. In XLDSP, if you are not working in Simulink, you are working in M code. You are designing your system using MATLAB code. You are going to design your code based on your specifications, and then XLDSP is going to bridge the gap between your MATLAB environment and your ISE environment. So again here you are going to here write your code in the form of MATLAB code, and you can simulate your design here, and then this can be easily transferred to your FPGA environment. Another very important here aspect in this one is your HDL co-simulation. This is very important part in simulation. So in this co-simulation, we can compare our simulation from software environment, and we can compare our simulation with hardware environment. So here you can see that one simulation is this simulation is basically from software, and this simulation is coming from hardware. So we can get simulated waveforms on our screen from software, and we can have simulated waveforms from our hardware environment on our screen, and then both these waveforms can be compared with each other by using this hardware co-simulation. So to explain this one further in detail, I have one video here. So this is the video. You can see that in this one, and here you can see that we have this is one system generator block. Again, these are system generator blocks, and apart from these, we have some other blocks from Simulink. These are blocks from general libraries of Simulink. So this is basically example of your hardware co-simulation. If here you can see that this is the example for FIR filter. Here we are using one random source as input, and wherever you just see these type of symbols, these are the blocks from your system generator library, and whenever system generator is loaded on your MATLAB, then only you can get these blocks. So we are taking this random source and we are taking this gateway in. This gateway in is nothing but it acts as ADC. It converts your analog signal into digital, and here you specify the number of bits you assign with your input signal. If you assign 16 bits, then your analog signal, it will be converted into equivalent 16 bits in terms of zeros and ones. Then here is your FIR filter block. Here in this FIR filter block, you are going to give the specification of your complete design, whatever design specifications are there. So sometimes when you take this input from here, and in case of filter design, you are going to multiply this input with coefficient values of your filter design. Let us say you are multiplying your input of 16 bit with the coefficient of 16 bit. It result may come in 30 or 32 bits. So the result of that will be stored in your accumulator of 32 bits. So output at this part here you will get in terms of 32 bits. If you want to use all those 32 bits straight away, you can send that to gateway out. Otherwise, you can, if you want to reduce the number of bits from 32 to 16, like if you want to use input and output precision of 16 bits, you want to use 16 bits for your input of your filter, and you want to use 16 bits as output of your filter, then the output of your FIR filter, this one here, and because it is in 32 bits, you have to first convert that 32 bit output into 16 bits. So that is why we are using here this converter. It is going to convert that output into 16 bits, and those 16 bits will be processed by this gateway out. As you know that gateway in is just like your analog to digital converter. It converts your analog signal into digital. Likewise, this gateway out, it performs the reverse process. It takes the digital signal and it converts that digital signal into its equivalent analog form. So this is the complete, you can say, working of this model. And here, this is the multiplexer where we are using output of our FIR filter, and this is the input you are getting from your random source. And we are multiplexing them, and we are monitoring this on our spectrum scope. So this spectrum scope is going to give you the output waveform that is coming from the software part, means from PC. And this complete structure is also implemented here in FPGA. This is nothing but this is your FPGA part, and here it is everything is implemented in terms of FPGA. And this part will work only when you connect your board with your PC. If your board is not connected with your PC, then it is this basically complete structure is not going to work. So your FPGA board, it should be connected with your PC, and then here you can see that output of your FPGA again, and again we have one input, same input of our signal, random signal, multiplex together, and there is one scope, that is spectrum scope 1. So spectrum scope 1 is going to give you the simulated output of your FIR filter. So you will get software kind of output from spectrum scope. You will get hardware output from spectrum scope 1, and in order to check the comparison between these two outputs, whether this output from your this software is similar to your output that is coming from hardware, we are using one more spectrum scope here, spectrum scope 2. And here we are comparing the software output waveform with our FPGA output waveform. So this is the complete explanation of this complete design, and now we are going to run the simulation. Here when we run our simulation, so we are running the simulation. At present, FPGA board is not switched on. It is connected, but it is not switched on. So our simulation is running. You can see the first window, and we are going for this. You can see that hardware co-simulation, and here now you can see that the error. So error in opening programming cable. Here you can see that error reported by sysgen. So it means that if you want to view the simulation, your FPGA board, it should be in on position. So after that you made this FPGA on, and again you have to simulate your design. Now again it is getting simulated. So here you can see that. Now here you can see that this is the output of spectrum scope 2. Means comparison of software generated and hardware. This is basically low pass filter, you can see that, and this is the comparison, green one. This is output of scope 1. It means this is the output of your FPGA, and scope, this is the output of your software. So three outputs are there. One is from spectrum scope, and another one is from spectrum scope 1, and this one is from this is the comparison between these different outputs. So from this so that was actually that demo was almost complete. So you have just observed that the red color output was from your spectrum scope, that was from your software, and your and blue color output was from spectrum scope 1, that was from FPGA, and green color output was from your that was a comparison between your software generated output and FPGA generated output, and that complete green color, that indicates that there was complete overlap between your software generated output and your FPGA generated output. So this was one demo of your this hardware co-simulation. So with the help of this hardware co-simulation, you can easily check your or compare your design with software generated design with your hardware generated design. So this was all about your front end VLSI design. Then we are moving towards the back end VLSI design. In backend VLSI design also we have actually it depends from software to software. Flow changes a bit according to vendors, but more or less it remains same. And here I am going to give you the exposure of your microwind software. What are the different steps involved in microwind software? And we also we have arranged demos for your cadence software also, it is there. So this flow is basically for your microwind software, and with slight changes you can easily manage in different softwares. So here again in microwind software we start with schematic design, and then this one, you design your circuit in schematic, then you convert Verilog file from that schematic, and then from that Verilog file you can generate the layout. So again, there are different options. Either you can automatically generate your layout, or you can straight away work on your layout, or you can straight away work on your HDL. So where to work, it depends upon the input with your designer. If you have the circuit in terms of transistors and logic gates, then no doubt you have to start with this schematic design. If you want to start, if you have a Verilog file with you and you want to work, and schematic is not there with you, in that case you can start from this second step, but the condition is your that HDL code, it should be compatible with your software. Means each and every software, it takes their own you can say HDL codes. They never accept codes generated by any other software. So so that is why all the vendors these days, as I told you, different vendors are there. We have Cadence is there, Synopsys is there, and then you have that Mentor Graphic is there, then Microwind, Tanner. So all these vendors, they provide at present, they provide complete solution. They provide complete solution, and you can use that complete solution. For example, when you generate VHDL using your Cadence software, that VHDL can easily be VHDL or Verilog. It can easily be used for your backend part. You can move from front end to backend side. So HDL code compatibility is very important. And the third part is your layout design. Layout design is basically straight away you are working on layout part. If we at present, whatever we are doing in our institutes, we do research in VLSI design. Actually, we go ahead with our CAD part, and our end result is going to be layer of masks. Layer of masks in terms of you can say N type mask, P type mask. You will get that layer of mask, and by using those masks you can fabricate your chip. So in our institutes we work up to this CAD part, and that is computer aided design, and rest fabrication or CAM part, you can say it is based on different industries like SCL. They are making their own chips. So if you have completed your CAD part and you have those masks with you, you can go ahead with your fabrication part also. So in layout design, straight away you work on your masks. You create again here you can use inbuilt transistors in terms of NMOS, PMOS. One flow is complete automatic flow. You are starting from schematic. From schematic you are generating the Verilog file, and that Verilog file will be converted into its equivalent layout design. This complete flow is basically you can say automatic control flow. Next step, you can start with HDL, but it should be compatible, and then you can generate layout. Third step, you can straight away you can work on layout part, and in layout part again you can take inbuilt transistors. Already some transistors are there in the library. You can use those already in fabricated transistors in terms of NMOS, PMOS, or you have the option you can make your own transistors also. Whenever you are going to go ahead with your by making your own transistors, it means that you are now working in basically you are going to design a custom ASIC. Means you are starting from scratch and you are making your own transistors in that case. So in this Microwind part, you can see that here we are starting with schematic design. So this is the design of one inverter. You can see that this is our PMOS here, and this is NMOS. By using PMOS, NMOS, we are making our inverter, and by using this inverter, this is basically first part, schematic part. We are designing schematic of our inverter. From this schematic, you have to create what? You have to create the HDL file, and that HDL file will be in the form of Verilog, and that Verilog file, here you can see that this is the Verilog file, And this Verilog file is nothing but it is basically giving you the description of complete net list, means what are the different components used in your design. You can use these complete description. NMOS is there, PMOS is there, what is their size, and what are their connections, where they are connected. These are different connections of your transistors. So all these kind of information you will get from this Verilog file, and this Verilog file is basically generated from your schematic. So once this Verilog file is there, then we call this Verilog file and our you can say microwind environment. And in microwind environment, based on this Verilog, or you can say sometimes we call this file as DEC file also, or spice file. And this spice file is used for designing your layer of masks. And this is the basically view of your layout. This is a layout view. Here you can see that. And this is complete view of your layout, where we have different layers. You have N diffusion, you have P diffusion. Red color is used for, this is for your polysilicon. You can see that this one, this red color is for polysilicon. And then these are contacts. And then blue color is used for metal 1. And if you have more than one layers in your design, then we can use second metal layer, right? So likewise you get this basically this is the complete layout of your inverter design using microwind software. And it gives you different masks, and your mask can be your N-well mask, your N diffusion, P mask, then polysilicon mask. By using all these masks, we can create these areas on your silicon. And then by creating these areas on your silicon, you can come up with your chip design. But that part is basically fabrication part, and mostly that is done with the help of the industries, where they support fabrication of chips. So this is your complete design flow of backend with the help of microwind software. So now overall conclusion of this session. So designers can have different options depending upon the input. If you are going to design ASIC, then you have to work in backend VLSI design. If you are going to program the FPGA, then you have to work in front-end VLSI design. You should have knowledge of the platform, is whatever platform is available with you. For example, if we are working in front-end VLSI design, then you should have complete details of the FPGA, whether you have Spartan FPGA, Vertex FPGA, or Altera FPGA, and what is the requirement, whether that FPGA is sufficient for your design, means all you can complete your design within the allocated resources. So all these kind of inputs will be there with you. And if we are working on backend VLSI design, then again you have to find out on which technology you want to work, whether you want to work on 180 nm, 100 nm, 65 nm. So that again depends upon the circuit you have, what kind of circuit you have with you. And most important part is whether you are working on backend VLSI design or front-end VLSI design, you should have software, supporting software for that. For front-end VLSI design, you have ISE software, and complete ISE suite is also there at present on the net. And for backend VLSI design also, you should have that supporting software. So by having these kind of inputs, and by opting any one of these options, so actually in VLSI design, the main problem with us is we always fear about the means how we can go ahead. But these days tools are so user friendly, and if we have the knowledge, we have the flow knowledge of each and every tool, then you can easily go ahead in your complete VLSI design. So there is no need to worry about the design completion. Each and every sport means most of the softwares they sport very friendly. So I will suggest or I will advise all our participants to go ahead with the flow of different softwares. You can have their user manuals, you can have complete flow of those user manuals, and then by using those user manuals you can easily go ahead with your complete design. So that's all about this complete session. These are some references. You can also um, refer these. Some books are there by Neil Veste, and then one book is by Wayne Wolf. Hello. Again, some user manuals are there by ISC, System Generator, Excel DSP, and these are some references. So that's all about this session. Now we are making this session open for queries. If you have any queries, so you can go ahead.
Hello, good morning, sir.
Good morning.
Sir, I am Prachi from GTVIT Delhi.
Please, just one query at a time. Yeah, please.
Sir, I want to ask one question. Can you please explain the steps of...
Please, please ask question one by one.
Sir, I'm...
कौन से कॉलेज से? Yes.
GTVIT Delhi.
Okay, you are from Delhi, right? Please go ahead.
Sir, my question is, what are the basic steps for hardware co-simulation? Steps, how can we can reach to hardware software co-simulation?
Hardware co-simulation basically, first of all, you have to load this system generator on your computer, and for that you should have compatible software. Compatibility is very important. For example, if you have MATLAB 7.4, at present MATLAB 14.1 is also there, so other MATLAB are there. So you have to check the compatibility of this MATLAB software with your system generator. I'm just giving you one example of MATLAB 7.4. That 7.4 is compatible with system generator 10.1, right? Once your this ISC is compatible with your MATLAB, you can download, you can load it on your PC, and then you can go ahead with your design, and you have to configure the device for hardware co-simulation. That is the most important part. On whatever FPGA you are going to select, you have to sometimes those FPGAs are automatically there in the list, but sometimes you will not get that particular FPGA in the list. So in that case, you have to configure the FPGA, and for that configuration you should have knowledge of clock pin of your FPGA. That is the only one important thing. So that knowledge is there, you can easily go ahead with that co-simulation part.
Thank you, sir.
Okay, thank you. Next.
Yes, sir. I am from IIT Gorakhpur.
From
Gorakhpur.
Gorakhpur. Okay. Please go ahead.
Sir, my question is, suppose we design MOSFET or any device using VSDL or Verilog. We have to use this device on any software related to microwave design. And can we interface this?
Interface what?
The design coded in the VSDL or Verilog, and we have to use that design in suppose HFSS or ADS related to microwave design.
Yes, yes. At present, Cadence Virtuoso, they are providing this compatibility that can be combined with your HFSS also. Yes.
Good morning, sir.
Okay, thank you.
Good morning, sir. Myself,
Good morning.
I want to ask a question that could we run HSpice code using Cadence tool? HSpice code using Cadence tool, can we run that code?
Actually, your query is not clear. Please repeat it.
Could we run HSpice code using Cadence software?
Yes, HSpice basically HSpice is one you can say it is general kind of code, and it is used by each and every vendor. Whenever we say about SPICE simulation is it is based on your HSpice only. Spice simulation is the basis, and by using that spice simulation, and each and every one vendor is using the spice simulation, and they are adding more, you can say, features to make that software user friendly. Means it should be easy for the user to complete the circuit. Spice is used by every software, whether it is Synopsys, whether it is Cadence Virtuoso, or it is Mentor Graphics, or your this Microwind Tenor. So it is used everywhere, just they are adding the more features to make it more user friendly.
Thank you, sir.
Okay, thank you. Yes, any other query?
Very good morning, sir. This is Niti from ABS Engineering College.
From
ABES Engineering College, Ghaziabad.
Ghaziabad, okay.
My query to you is that we are basically talking about the structure starting from the front end. Now my question lies that if I'm doing a structuring using VHDL or Verilog coding, and then finally when I'm going for a layout, then where that conversion is happening, like where that transfer level thing is coming in.
At present, you are working in ISC environment?
I'm sorry, sir?
At present, you are working in ISC environment, means you have written your code in VHDL and you have simulated that code in ISC, and you want to move towards this one backend?
Basically, I want to understand that where the conversion thing will come. That from where my VHDL, and if I'm writing a code in VHDL and Verilog, right? And then I want to make the layout for my entire structure. Then where that thing will come.
Okay, means you want to create layout from VHDL.
Yes, layout from the VHDL. Is that possible?
Okay, right. Basically, as I told you, each and every vendor at present provide complete list of tools at present. So you can, for example, if you are working in Cadence, you are if you are designing VHDL, in earlier days for layout creation only Verilog was supported. But these days, some vendors, they are also VHDL is also supported, and we can use VHDL also for your this layout generation. The only thing is that vendor should be same. Means if you are generating VHDL by using these Cadence tools, that can be easily ported to layout design by using Virtuoso. Means if you are using changing the vendor, then it is not possible. Means compatibility should be there, then you can easily go ahead with your front end design to back end.
So that means right? There will be some kind of a conversion thing that will be happening in the tool itself, right? Initially when I make my code, and then really I can have the layout of this.
Actually, that conversion, whatever conversion we are saying, each and every vendor is having library, their own library. Software changes because of their own libraries. Each and every vendor provide their own library. Their own libraries may have different components in the library, and one vendor may provide component 10 components for one particular architecture. Another may provide 20 components for that same architecture. Another vendor may provide 40 components for that architecture, right? So means 40 options, more options are there for one for implementing one main particular thing, right? So whenever we go from VHDL, basically VHDL is nothing. VHDL will be converted automatically into RTL. RTL is your register transfer level. Basically, you are converting your this textual language into schematic part, right? You are going to convert it in RTL, register transfer level, and then you are going to map your complete circuit with the components present in the existing library, right? So because mapping will be with existing library, that is why that is going to map according to their own vendor availability. If mapping is on Cadence and we are going to implement it on Mentor Graphics, it is going to give you the problem. If it is for Cadence and we are generating layout by using Cadence only, then it will easily it is going to create the layout part. Basically, VHDL will be converted into its RTL. It will not remain VHDL. That is just one kind of input that we use for our system design, right? So if any other query is there, you can ask. Otherwise, we can move for T.
Well, I am from the Madam University of Technology.
Yes, please.
Can we generate the Verilog model from Verilog?
Verilog model from?
simple box again, if we are using
Yes, means you want to generate Verilog from system generator. Simulink in system generator.
yes, sir, last time we are using, but I am not running the Verilog model on the
In Simulink, actually, you can use system generator, and in system generator you have both options of HDL. You can go for VHDL or you can go for Verilog also, right? Yes. So I think we can move for tea. So we can have now 15 minutes break, and we will be back after. So we have half an hour time. So our next session will start at 11:30. So I request all the participants to be there around 11:20 so that we can start our session sharply at 11:30. Thanks very much.
काम मान किया था अच्छा आपको भी पता था सुने आप कहाँ जा रहे हो मैडम यहाँ बहुत ठंड लग रही है बोले कि लाइन पैरिस के लिए बैठने क्या कहाँ जा रहे हैं आप ये नहीं जाना पर नहीं ना आप तो करो चलो ये भी चल रहे हैं खाना ना आओ मैडम मैं फोन करके मैंने सोचा और तू क्या था केमिस्ट्री भी दिल वाला लगे होता है मौका मिलेगा तो देख कर पार्टी कर रहे हैं जो ऊपर जीवा शक्कर नंदी वालों को बदले पैसे दे रहे हैं आपके फ्रेंड्स
वाली साहब वो चले गए यहाँ से
चलो निकलो पहले ये काम जरूरी है रीमेल वाला फॉर्म भरो पहले अपना ठीक है अब डाउट है आप देखना चाहिए मुझे जाना आपको क्या टाइम तो नहीं बता सकती थोड़ी देर में बनाकर
suppose बनाओ she know what undertaking form means इसी में लिख दिस undertaking सही फॉर्म है ऐसे ना मैं और मुझे वहां पे कल से undertaking लेके आएंगे खाली हां इतने बच्चे किसमें किसी के पास होएगा undertaking फॉर्म तो फिर किसी पे बना के तो कर देंगे नहीं जब undertaking आएगी तो फिर छोटा साइज ले आप गिफ्ट दे देंगे पूरी टाइट गिफ्ट दे देंगे वापस करके कब तक और साल में करना मुझे बड़ी बात नहीं है अच्छा है कि ऐसे गिफ्ट दे देंगे आशना होना के बाद हम आ सकते हैं फाइनल चैप्टर का फॉर्मेट जो होता है वही रहेगा इसकी बात कर रहा हूं मैं वो देख ही सकते हैं क्या था आगे कैसे मैंने इसलिए ना कहते हैं मेरे को जो पुराना था नहीं उसमें क्या होता है कि जो एमबीए में तो उसका फॉर्मेट अलग होता है बीसीए का अलग होता है फिर हम बीसीए का भेजोगे ये तो गारंटी है जो गारंटी अगर आप मतलब आप जब कोर्स का बनाते हो ये बीसीए कोर्स में बनाते हो खाने को सब करते हैं वीडियो वाले तो उसमें फॉर्मेट होता है ये मैं कैसे तो खाने की फॉर्मेट तो अलग होता है इसलिए शायद कोई मैं पैन नहीं अभी फॉर्मेट नहीं चल रहा चल ही नहीं रहा चल ही नहीं रहा अभी इसमें है फाइल या एक और अब इनकी इन्फॉर्मेशन रह गया ना फिर हम शीट बनाते सब नेम ऑफ द स्टूडेंट प्लस इनकी फंक्शन खाली आता है मतलब सब कुछ खाली है मींस ये फंक्शन फॉर्म वो एक पेज नहीं करेगा नहीं करेगा नहीं मतलब वो अलग से शीट बन जाएगी ना एक लेक्चर लग रहा है मेरे लेक्चर And these are इतनी मोटी हूँ मैं इसमें तो और ही लगती है तो वो आपको तो मेरे लिए रिजेक्ट क्या एमएससी लेने वाले मैम उसका ना पैटर्न आप देख लेना रेफर कर लेना एमसीए के ना जो क्वेश्चन पेपर निकालता है पीडीयू का ठीक है पीडीयू क्या अटेंडेंस का क्या आईडी क्या आईडी का आईडी अमन शेख वेडनेस कब तक ये बार ऑब्जेक्टिव टाइप क्वेश्चन ना 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 सीधा पीडीयू का बच्चे की वो है ना एक लड़की को रहती है बोल रही आज मूवी में कल हो जाएगा ना कल फाइनल है ना क्या मैम प्रेशर पार्टी का बात आस्क करना मैम प्लीज आप मुझे बता नहीं थे मैंने बता सबको अपने जूनियर से क्योंकि मैं खुद अरेंज भी जानती हूँ तू चाह रही थी करके मैं ना मुझे आप बना रहे हो देखो मैं बात करूँगा पर मैंने बोला था मैंने कहा परसों नीसा मत भूलिए ट्वेल्थ को एमएससी का फाइनल है ट्वेल्थ को ट्वेल्थ को पूछना नहीं है सब्जेक्ट है एमसीए को फिर आप मटीरियल पड़ा है मेरे पास पढ़ाने वाला माइक्रो प्रोसेसर वगैरह मैं बोला ना एमसी को आगे एमसी को अभी रियल ये हमारी ऑनलाइन सब कुछ होती है कैप्टन में और मैंने बोला डीसी हां फिर मैं डीसी का क्वेश्चन पेपर निकालूं वहां से कैप्टन में आपके भी मोड का फॉर्मेट ऊपर तो लिखा ही होता है ज्ञान से वो तो होगा ही है Okay. मैं बोला नहीं सुनो प्लीज थोड़ी देखी इसने की है कंप्लीटली ना नहीं कंप्लीट करवा दो शाखा मेरे को चलने वाली काम भी है फ्रेंच हाँ फ्रेंच तो आने फ्रेंच की जो भी तो एक होती है ना मतलब वेट होती है ना सारी काम मतलब मतलब शायद आती है नहीं आंधी है शायद आंधी मैंने कॉलिंग को मतलब सुनो सुनो तो बीसी को करना होगा ना उसके बाद वीडियो नाम बैठ ना करना मैं कितनी बार उसके सामने ना चलते हाँ बीसी से लाते बीसी नंबर होती है उसके 8 क्वेश्चंस वाले होते हैं बीसी सिर्फ 8 क्वेश्चन होते हैं आपने अंदर 3 से 5 वाले होते हैं ना अंदर ये सेक्शन भी करवा देती थी हां अलग अलग मैं फिर मैं कंपटीशन में भी मिलता करता है तो पहला मोड मैंने साथ में चलो इसको कर दिया यार 7 से हम लेक्चर ले जाना है फिर यार मैं इससे बना लिया उससे फिर यार नहीं करेगा मैंने फोन करा मैं भी बना लेना मैं एक ना पीडीएफ का पेपर मेल कर देती हूँ बीसी को ना उससे अकॉर्डिंगली बना लेंगे यहाँ पे परसेंट आपका भी तो आपको मिलना है एमसी को डाउनलोड कर लो यार पेपर एक प्लीज ऐसे क्यों कर रहे हो क्या मैं मॉर्निंग में बात सुनो वो जो लेटेस्ट वाले जो आगे हमने करना ना पीपीटी है ना वो लेके ना नीचे आ जाओ वाले लैब में मैं यही पढ़ा दूंगी हेलो आंसर तो सबको देना होगा मैं पहले आता था नीचे आता थोड़ी बनाई थी एक कुछ मतलब फ्रेंड थे पर कहते मेरा बस आ गई थी मैंने बस आने वाली थी मैंने यार उनकी मैम को कॉल करी जाके मैं बोल रही मैं गया बस चले गया हैप्पी बर्थडे बर्थडे बना दे बर्थडे हम ये लगे ना अपने बर्थडे का विश नहीं किया हेलो मैंने तो देखो ही नहीं है कल आएगी क्या जवाब कर जवाब ओके ओके हाँ जी ठीक ये बैठा भूता ना अश्वा में करता पैटर्न क्या नहीं करता कैंसी लटक में आ रही है नीचे वाली
NC is also कर देते हैं इसमें क्या जावा का ही कर दो जी क्या RDBMS भी कर जावा या वेलकम जी PC वाला ही है सॉरी
अच्छी का चलो वो गया फिर वो आगे सर आ चुके हैं मैम आ चुके हैं दोनों से फिर एक एक्स्ट्रा रोपड़ IIT रोपड़
सर मैं ना एग्जांपल देता है क्योंकि मैं अपने सब्जेक्ट का देखना है पता नहीं ना मुझे तो सर वो MBA का यूनिट वाइज आता है BCA का नहीं होता यूनिट वाइज मुझे नहीं पता सर इसका उत्तर अपने आप पूछ सकते हैं अगर मैंने कभी भेजा सेंसर मांग रहे थे मेरे पेपर का पैटर्न ऐसे आ रहा था मुझे ऐसी चीज कोई टेंशन नहीं मैं देख लेती हूँ बाकी सेमेस्टर्स का भी देख लेती हूँ BCA यही होता है HPC को मैं पेपर हुआ 11:30 मैंने कर दिया
कृतिका मैम प्रेजेंटेशन ਜਿਹੜੀ ਹੈਗੀ ਹੈ उसको क्रोम नहीं करना क्रोम चलाना
देखो इनकी लैब देखो कैसी और मॉनिटर भी लगभग ये लैब नहीं लग रहा मुझे तो फैकल्टी का केबल लग रहा है लैब है ये 22 इंच का मॉनिटर है लगा देना उसमें
आपने कहा है सारी रसीद जितनी भी आप सामान होगा ना कैंटीन में कहते हैं कि इकट्ठी करनी है लास्ट में गौरव सबको देते हैं ठीक है आप नहीं जाते वहाँ पे कोई बात कर सकते हैं सामान जाते हैं
So good morning. We are going to start our second session on high-speed interconnects, which will be taken by Dr. R.Y. Sharma. Let me tell you brief about Dr. R.Y. Sharma. Dr. R.Y. Sharma is an associate professor in the electrical engineering department at IIT Ropar since 2012. Before joining IIT Ropar, Dr. Sharma was a postdoctoral fellow at the Interconnect Focus Center, Georgia Technology, Atlanta. And prior to this, he worked as a postdoctoral fellow at the Design Automation Lab, Seoul National University, Seoul. Dr. Sharma received the BE degree from North Maharashtra University in 2000 in Electronics and Telecommunication Engineering, the MTech degree from Dayal Bhag Educational Institute in 2003 in Engineering System with major in microelectronics, and the PhD degree from JP University of Information Technology in 2009 in Electronics and Communication Engineering. His current research interests include design of high-speed chip and 3D interconnects, 3D IC design, and graphene-based nanoelectronic devices and interconnects. He is a referee for several journals, including IEEE TEMC, IEEE MTT, IET MAP, Micro and Nano Letters, Journal of Supercomputing, Journal of Computational Electronics and Integrations, the VLSI Journal, and has served as a committee member, session co-chair for multiple international conferences. He is a senior member of the IEEE and is currently on the board of IEEE Delhi section EZICOM. So I invite Dr. R.Y. Sharma to engage the session. Dr. R.Y. Sharma.
Thank you for inviting me here, first of all. I hope I'm audible. So basically, I'll be talking about why do we need to design efficient wires, and what is its implication on next generation ICs. Now, basically this figure that is there on the first slide tells a lot of things. Assuming that we have a transceiver circuit wherein this is your transmitter and you have a receiver, then actually there is a wire that would transmit signal from the transmitter to the receiver. Till very recently, what was the trend was that a lot of research used to be done on device modeling, on improving the performance of devices, improving the performance of circuits, and also on the fabrication related issues. But wires, or interconnects as we call them in technical literature, was slightly ignored. The reason, of course, was that people thought that it is only a media to communicate signals from the transmitter to the receiver, and therefore at best we can leave them. But the situation worsened over the period of time. The reason, of course, is that, as we all know, there is a Moore's law, and Moore's law basically dictates that every couple of years we increase the functionality, reduce the device footprint, circuit footprint, etc. And as we are improving the performance of devices every Moore's cycle, what is happening is that the wire performance also needs to be improved. Otherwise, it would act as a bottleneck. And if that is the case, then in such a scenario, if I were to put it in a very simple layman's language, today I am sitting in Chandigarh, and if I have to catch a flight to Bombay, it probably would take 2 hours for me. But from the place where I'm delivering the lecture to the airport itself might take me more than a couple of hours. So the bottleneck in this case is the connecting road from here to the airport. Now, using this analogy, we can try and correlate it with the performance of a device vis-a-vis that of an interconnect. Well, device performance is improving dramatically. If we do not catch up as far as the interconnect performance is concerned, then what would happen is that the interconnects would become the bottleneck and will bring down the throughput of your entire integrated circuit or a system. With this brief thing, I would start with my presentation, and to give you, because I believe a lot of students are coming from varied backgrounds. Some of them might be from microelectronics background, some may be senior UG students. So I'd like to initiate you to this area of high-speed interconnect design, and we'll start with the basics, understand how to model interconnects, and then somewhere at the fag end of the presentation, I'll leave with a couple of relevant current research trends that are important for our, for our PG students or our PhD students. Okay, let us start one by one. I'll just share a few slides with all of you, and I just expect you to guess. This is the first computer that was ever made. It was a mechanical computer. It was called as the Babbage engine or the Babbage difference engine. It was a mechanical computer, and what it could do was only simple arithmetic computations like plus, minus, multiplication, division, etc. It had a lot of moving parts, actually 25,000 moving mechanical parts, and it costed a fortune. It was built about 200 years back by Charles Babbage. Then let us look at the other thing. Then we move to the era of electronic computers. And this is the first electronic computer that was ever made. It was called as the ENIAC, and the ENIAC was made in 1946. As a matter of fact, it was bigger than the size of conventional halls or rooms. And this gentleman who's working here is actually working on a memory card. This is one memory card. It was made out of vacuum tubes because in 1946 transistors were not invented, as a matter of fact. And then came the era of solid-state electronics. In solid-state electronics bid farewell to vacuum electronics or vacuum-based devices, and the first solid-state electronics device that was made was a transistor. The transistor was made in the AT&T Bell Labs, as we all know. It was made by Shockley, Bartin, and Brittain. They were subsequently awarded the Nobel Prize in 1947, and it made a sea change in our approach, in our way of designing circuits and electronics. This was the first integrated circuit that was ever made. It was, as a matter of fact, a very simple gate level circuit. It was made by Motorola in 1966. Had a few dozen components or transistors on it, and that's it. And then came the era of the microprocessors. Microprocessors, basically, if we were to understand, represent some of the most complex digital chips that are ever made. This is, as a matter of fact, the first microprocessor that was made. It was 4004, a 4-bit processor. It had about 1,000 transistors, and its operating speeds or clock frequencies were about a megahertz. This was made around the early 70s. And then this basically represents the current microprocessor that most of us are using. It's on my laptop. Most of you are using in your smart devices or laptops. This is a multi-core i7 processor. It is part of the famous I series of Intel. It's a quad-core processor. As you can see, there are 4 cores. There is a queuing register. There's a memory controller. It's a very complex design. There is a cache on the chip itself, and you have various peripherals, IOs, etc. that are available. The take-home message, of course, here is that it has close to the population of India in terms of the transistors sitting on a typically 2-inch by 2-inch wafer, or even less. So such is the device density. And if we move through these slides, what we understand is that unlike any other industry in the world, this is probably the only industry in which you have, you're getting more, still you're paying less. Let us compare with, let's say, conventional industries like the automobile industry. And in the automobile industry, if you want to buy a luxury car, you would have to probably pay more. But that doesn't happen in the semiconductor industry. In the semiconductor industry, we have more, but we have to pay less for it. And the reason for this, of course, is that there is a highest level of integration. There are a lot of processes involved, a lot of automation involved. If you look at the current processor, as a matter of fact, you would see that almost 1/3 of the periodic table elements are used. A few hundreds of processes are used to finally come up with this IC. So it's a complex thing, but it's a challenging thing. And in the overall chip design, if you see, there are multiple components. You have to optimize the performance of your device, you have to optimize the performance of your circuits, and you have to optimize the performance of your interconnects. Only and only then you have a situation where you have the optimum performance, you have gigahertz, and it's in terms of digital design. Okay, in mind, one thing that should be clear to our audience is that unlike any other industry, we are talking about an industry where it's far more complicated to come up with the next version, because we are driven by consumer demand. I mean, let's imagine a situation where every September we wait for the next iPhone to come, and the first thing that we ask from the manufacturer is, what more do you have to offer compared to the version that you just made a year back? So it's a very complicated scenario. All right, and this is because of a gentleman called as Gordon Moore. Now what he did was he made a prediction, and it's not a law, but it's in most literature it is commonly known as a law, and I'll tell you why it is not a law. Gordon Moore was sitting one fine day and he was scribbling some notes, and what he figured out was that roughly 1.5 years to 2 years we would have all right. Okay, I think now it's visible to most of us. Earlier it was not visible. Okay, sorry, I think you missed out some of the slides, the audience on the other end. I'll very closely, very quickly go through these slides. I had only covered a. Okay, sure. Okay, so I'll start with Moore's law again, and as a matter of fact, he predicted that every couple of years or slightly less than that, we'll have the productivity of our chip or our integrated circuit doubling itself. And basically what we have done is that we have made it sure that the industry follows this as something sacrosanct. So what we are doing is we are trying to meet the Moore's prediction. Of course, there is a commercial angle to it. Unlike any other industry, this is one industry which is heavily driven by consumer demand. And the consumer asks for more every next year. They ask for more things, more functionality, more productivity in general. So for the industry, it makes sense if they can keep up with the Moore's prediction of doubling their capacity every 2 years, because then revenues are linked accordingly. Okay. In the next few slides, I'll just quickly go through what this Moore's law was. But before we do that, just a quick clarification here that it's not a law, and as I said, I'll come back to it. The reason why it's not a law is because a law is has a scientific logic to it. In this case, it was more of a prediction. So for example, V equals to IR is an Ohm's law. That's a law. We can scientifically prove it. Moore's law is not a law, it's only a prediction. It's a different matter though that the industry is following it more like a a kind of a dictum that they have to stick to the prediction, because as I said, it has some commercial angle to it. Alright, so as per the Moore's law, what was predicted was that your number of transistors or components per integrated circuit would double itself, and then if we were to plot it over over the number of years, it would come out to be a linear scale, which is shown in this slide here. And because of this, if you are having more transistors, you will have more complexity, because you will have more functionalities to be incorporated, and therefore the design will be very complex. So how complex is it? As a matter of fact, today's circuits are more complex than a human DNA. And this is very well illustrated in this figure, that as we move up the ladder, you will see that, let's say, the number of bits per chip, then the memory storage is more than that of a human DNA. So it's very complex design. It requires a lot of engineering, a lot of science behind it. The transistor count historically, now this is a historical curve, this is not a prediction. What we have done in this slide is essentially the number of transistors per processor we have plotted, and as it turns out, if we connect these dots, it is more of a linear line. Now, the base reference here is the processor. The reason why we are taking the processor as a reference is because, as I've told you earlier, the processor is one of the most complex digital designs. So that's our benchmark, right? Starting from 8086 all the way up to the historical 286, 386 series, then the Pentium series, and now we have the I series. Of course, this source is from Intel, but it applies to other processors also. And somewhere close to about 5 years back, we actually crossed the 1 billion threshold. So as of now, our commercial processors have number of transistors equaling the population of our country. It's amazing. I mean, if you look at the design complexities. Now try and understand, if I have a billion devices sitting on a 2-inch wafer, then these devices have to be connected. Then imagine the wiring complexity, and also imagine the type of wires that are required. We require, each device is an active device, and therefore we require a separate power and ground connection to each device. So we have two types of wires there. Then these wires, or these circuits rather, will process some data. Therefore, I need a separate dedicated wiring network for data. And finally, in most possibilities, these circuits are sequential circuits, and therefore they require clocking mechanism. So all in all, I have 4 different types of signals to be routed in these billion plus devices on such a small area. So we have wiring network for power, for ground, for data, and for data or signal, and for clock. So a billion transistors to be wired 4 times of that. That is the type of complexity that we have, and we'll talk about it in details as we move ahead. All right. Now, This is the same slide in a different way. It basically gives you a conclusion here, and the conclusion is that if I plot the number of transistors over all the processors and do some number crunching, it turns out to be that yes, the transistor count has actually gone up twice in almost about 2 years. So the industry is historically following the Moore's law. Okay. Now this is a very interesting slide that I want you to understand, because it actually tells you that while we are increasing the number of transistors on the chip, we are not actually increasing the die size. We are keeping it as the increase in that as incremental as possible. Now what we have done in this slide, essentially on the y-axis, if you see, the die size is observed here, and what we see is in about 2 years you have the number of transistors doubling itself, but the die size increases by only 7% per year, or let's say in one Moore's cycle 2 times, which is 14%. So my area of the chip has increased by only 14%, but the number of transistors has increased by double. So what I'm doing is I'm basically trying to compact my circuit further, which leads to a lot of problems. One of the problems, of course, is if you have more active devices closely packed to each other, then fabrication becomes an issue. And of course, if you can somehow fabricate it, heat becomes an issue, because you have now more active devices which are acting as switches, as a matter of fact, in a closed area. And therefore it becomes very tough to manage the heat which is generated in such densely packed ICs. And of course the frequencies have doubled over a period of time. As a matter of fact, if we start from the first processor, which was 4004, which had a frequency of about 1 megahertz, that is the clock speed, to the current processors which are multi-core and have frequencies close to 3 gigahertz, 4 gigahertz also, we see that there is a doubling of frequency practically every 2 years, if you take the average of increase in frequencies. So with frequency, what does it mean? That now my switches, which are my 1 billion devices, will be switching on and off at this rate, at 3 gigahertz, or 3 into 10 to the power of 9 times per second, right? And if they're switching on and off, and as most of us, if we have taken the fundamental courses on CMOS design, would have realized that every time the switch is on, it will dissipate some energy. It could be the static power dissipation. In case of CMOS, it is the static power dissipation is minimum, but then you have leakage power, number one, and number two, you have the dynamic power dissipation, which is directly a function of frequency. Now therefore the dynamic power dissipation would be pretty high, and that brings us to the next slide. As you can see, that the dynamic power dissipation in terms of watts is actually increasing per processor, and this is a major problem. Essentially, if I can see, the power dissipated by these processors is of the order of a few kilowatts. Now that is something which is unbelievable. I mean in a small 2-inch wafer, the power dissipation is alarming. It's alarming, and we have to find ways, and that is also one of the very active research areas where people are working. As a matter of fact, our friends from mechanical engineering are helping us out with their knowledge of heat and mass transfer, thermal engineering, etc. Okay. Now the power density is nothing but the power dissipated per square area, and what we see here is surprising, that today's processors, the power density is as high as that of a rocket nozzle which sends spacecraft to to outer space. It's unbelievable. I mean if we touch the microprocessor of our phone or our laptops or whatever, we won't actually get really hurt. But the actual power dissipation is so high, which means there are a lot of efficient cooling mechanisms that are involved here, and we need to really appreciate the efforts of our thermal engineers who are working in this area to make sure that this much of power density is cooled properly so that our devices and our systems, handheld devices, don't really malfunction. Okay. So what does this all mean? What it all means is that if in the beginning I gave you an example of the automobile industry, and I told you that, look, if we have an automobile every 2 years, I don't go to a Maruti or a Hyundai showroom and expect to give us, you know, double the luxuries and double the features at half the price. We don't really expect that, but we really expect that with semiconductor industry. Whenever there is a new S series phone or an iPhone or a new laptop or an iPad, the first question that comes is, what extra do you have to offer to us besides the aesthetics, besides the look, etc., etc. So we look for more technical capabilities other than of course the aesthetics, etc. What this all means is, if I were to apply the Moore's law on an automobile industry, it would have been something like this, that if I would have applied this and started making a Rolls-Royce car, then my Rolls-Royce car today would be costing only $100, which is about 6,000 rupees. It actually costs more than that. For 4 liters of petrol or diesel, it would be running for almost 1 lakh miles. And the speeds would be so high that the engine would be exploding once a year. So that gives us the you know, the type of efforts that our IC designers are putting in this particular industry. All right. So this basically sets the tone. We are now, I believe most of us are now on the same page vis-a-vis what it all takes to make a circuit, make an integrated circuit. And now I'll be talking about a very important factor, where actually our country can also contribute, is this, which is the productivity gap. So these are two curves actually, as a matter of fact, and you have the complexity in terms of the logic per chip, which is the blue line, and you have the technical staff in terms of the red line. And as you can see, there is a huge gap. And as we are moving towards higher generation processors, the gap is increasing, the productivity is coming down. So we as a country can definitely contribute, and as a matter of fact, India is coming very nicely as a design hub in the area of VLSI design. I was just browsing some job portals, and what I figured out is that VLSI, microelectronics, or electronics in general, is the second most sought after, in terms of vacancies on all these job portals after IT or IT enabled services. So that gives you the quantum of activity that is taking place in our country, and I think this is probably the best time to be in India if you are in this area. Okay, let us move forward and let us now talk about the technical part of my presentation. So okay, there is a problem. I have a billion transistors, and these transistors have to be wired. How do you wire them, and how do you model these wires? Why do we model these wires? This is what I will be talking about in the second half of my presentation. Okay, so what is a traditional VLSI design cycle? We all know, most of us are PG students in VLSI or microelectronics. I start with my system specs. I understand the functionality, the logic synthesis. We design the circuit, which is the schematic. After the schematic, we made the physical design. Then once the physical design is made, it is sent to the fab engineer. He fabricates it, packages it, and there are other things like testing, etc. What are the metrics on which the performance of an integrated circuit is evaluated? It's typically evaluated in terms of its operating frequencies or speeds, power dissipation, area, reliability, manufacturability, testability, design time, etc. So these are some of the metrics on which the performance of an IC is judged. Okay. What we have seen, and this is a very important thing here, is that as we move towards the submicron, deep submicron era, the interconnect performance, especially its delay, dominates over the device or the gate delay. So no matter how fast you make your circuits, remember the first slide where I showed you a transmitter and a receiver? No matter how fast you make or how efficiently you make your transmitters and receivers, it is this wire which is simply connecting these 2 points which will act as a bottleneck. And we need to optimize it. But before we optimize it, the first thing is, how do I find out the various parasitics of the wire? All right. Now in this slide, I have actually highlighted physical design as a, in bold red. The reason is because interconnects play a very big role in the physical design part in this entire design cycle. Okay, I'll talk about that in a minute. Okay, so what does a physical design basically do? Let's say this is a schematic. Excuse me. No, excuse me. Can you connect this to the power? पावर केबल तो लगा Okay. Okay, sorry for the inconvenience. There was a little bit of technical glitch. Okay, so let us say I have a schematic here. Now this schematic shown here, what does it do? It's basically a simple CMOS circuit. It implements some basic function. Let's say Z is equals to A plus BC plus DE. Then if the schematic has to be sent for fab, the first thing we have to do is we have to convert this into a physical design, which would look something like this, which basically tells to the fab engineer that, hey, look, for this, realizing this function, these are the actual physical attributes that needs to be taken into consideration for all these devices. And then we, of course, we come up with the base. There are various, for a complex circuit, this is of course a very simplistic circuit. For a complex circuit, we need to take into consideration partitioning, floor planning, placement and routing. And as I said, routing of wires. And as I've already written here, there are 4 types of wires. So you need to supply clocking, you need to supply data, and you need to supply power and ground. All right. So all of this, if done properly, then we come up with an optimum integrated circuit. Okay. So now this brings us to an important question: what are interconnects? So this is the schematic of a transceiver circuit. Then the schematic, then the physical part would look something like this. This is an actual SEM image wherein you have this as the wafer over which there are wires running like this and connecting the 2 ends of the transceiver circuit. Okay. Now why do we need to talk about interconnects? Because, and you need to read this article here. Basically what it shows is that as we move into deep submicron era, what we see is that the interconnect delay increases and actually starts. Total delay, of course, will be gate delay plus the interconnect delay, and it is almost increasing exponentially. So we need to understand what causes this delay and then optimize it. All right. Now, okay. Now, typically interconnects are always, there is an analogous term along with it, which is basically called as the high speed. So what is high speed? What does it mean in terms of actual technical content? So basically high speed relates to the speed of signal transmission or the frequency of the signal. It also talks in terms of the physical dimensions, particularly the length of the wire. Now this is something interesting. Most of you must have taken a basic course on electromagnetics, and if you remember transmission line theory, you can actually draw a lot of inferences from that. If you remember, there is a physical length of the wire and then there is an electrical length of the wire. So what is the difference between the two? The difference is this, that the physical length is of course in terms of millimeters or microns or nanometers or whatever, while the electrical length is in terms of the wavelength of the signal. All right. Whenever the wavelength of the signal, if the length is greater than a particular benchmark, then the wire could be termed, or the transmission line could be termed as a long transmission line. Otherwise, it's an electrically short transmission line. So that's the electrical length of the wire. And typically, the benchmark is that if the physical length, which is let's say L, is less than lambda by 10, it becomes an electrically short wire or interconnect. And lumped transmission line models are good enough to understand its behavior. However, if the physical length L is greater than lambda by 10, then the wire is, or the interconnect is an electrically long interconnect, and we actually require now distributed transmission line models to understand its behavior. Okay. Now, what does these high-speed effects basically do? They basically leads to a lot of problems, and these problems, if you summarize in a nutshell, are basically signal integrity issues. There could be, remember that basic control system theory in which we have a second order system and RLC system. So if I have a wire which has a physical length, definitely it will offer some resistance. There will be a line to ground capacitance, and if it's an electrically long wire, it will also have inductance. So in short, we are having an RLC kind of structure, and this RLC kind of structure will lead to overshoots, undershoots, reflections and ringing, and it's a major issue as far as signal integrity is concerned. What determines these signal integrity issues are listed here. One of them, of course, is the length. The other is the cross-sectional dimensions, how narrow or how wide they are. Then, of course, the clock speeds, very important. Also, what is important at these high gigahertz frequencies, the charge actually flows on the surface of the wire, and therefore skin effects plays a dominant role. And finally, these wires basically are made over SiO2, which is laid over a silicon wafer. So the dielectric properties and the losses because of the dielectric also plays a very important role, which is all enumerated here. Okay. What does the interconnect do? If there are a lot of parasitics, which is basically it has high R, high L or high C or all of them, then it will reduce your reliability, signals may get distorted, it may affect your performance in terms of power dissipation may go up, and especially for handheld devices which are powered by batteries, it becomes a major source of nuisance because you have to charge your batteries again and again, which means your overall throughput of that handheld device comes down, as well as your battery life comes down. The type of parasitics which I've already said is basically if you have a metal line which is running over a SiO2 kind of substrate, then you basically will have RLC, and these are the parasitics of any high-speed interconnect. Now, type of interconnects, there are a lot of ways to classify interconnects. You can classify based on their material, you can classify based on where they are used, etc., etc. And we'll just quickly go through some of these, classifications. You can have interconnects which are on-chip interconnects. So basically wires which are running on a silicon wafer connecting devices on, let's say, a processor or a memory chip or something like that. This is a typical SCM image. You can see here basically multiple layers of wires stacked all over, over one another. So it's a 3D IC, and as you go up, the wire cross-sectional area increases. And then you have chip-to-chip interconnects, and chip-to-chip interconnects basically connecting, let's say on a motherboard, it's connecting a couple of chips, the processor with the RAM stack and things like those. It's shown here. And finally, off-the-chip interconnects. So basically, if I have, let's say, if you remember, our typical digital electronics lab, which we did, we used to see there's a chip which has some 14 pins coming out of it. So those pins are nothing but wires in a sense, and at these high frequencies, they will also offer some parasitics. Right? Of course, in a real world scenario, we do not have those kind of pins coming out any longer. If you try and open up your laptops or handheld device and look at the processor, what you see is the processor has an array of ball grids, and it's flip chipped and pasted over the wafer or the board. So it's a flip chip array, and the interconnects are now solder bumps which are round in shape, and which is somewhere shown here in this image. So you have these, this is your, let's say, your PCB or your motherboard, and you have multiple chips stacked here, and they are connected through a BGA package. And these balls, solder balls, also offer some RLC parasitics, and therefore will lead to signal disintegrity. All right. So this is one way of looking at how to classify interconnects. Of course, there are other ways of classifying interconnects based on the material that has been used. So typically your interconnects are metallic in nature. Historically, aluminium over SiSiO2 was deposited. The reasons were well known, that as aluminium formed a very nice adhesive layer, so there was no reliability issues. But as we all know, aluminium's conductivity is lower than that of copper. So people were tempted to use copper as an interconnect material. But the problem, of course, was the moment you have copper deposited over SiSiO2, it would just sink or penetrate into the wafer. It's something like pouring water or ink over a piece of sponge. So how to avoid this problem? There was an entire process that was developed. The motivation for this process was taken from a century-old technique, and that technique was of how to make copper utensils. Now, if you remember, if you have to make a copper utensil, you have to make a mold, and that mold has to be that of clay. Now, clay has a lot of resemblance to that of silicon substrate because they all come from the same raw material. So this process is called as a Damascene process, and in Damascene process, which was basically developed by utensil makers in Damascus, Syria, they would put a thin seed layer on the inner side of the mold and then deposit molten copper. This thin seed or barrier layer would make sure that the copper doesn't percolate inside the mold or the clay, and therefore you can come up with whatever you want. The same technique has been applied, and if you can read a little bit about Damascene process, you'll understand how copper wires or interconnects are made over a silicon wafer. Before we come to that, of course, we have another way. If we don't want to have metallic wires, and this is a buzzword nowadays, is optical interconnects, basically photonics, nanophotonics, things like those. And finally, we have carbon-based interconnects. So carbon is a promising technology for conducting as a conducting medium also. So you have carbon nanotubes, you have graphene nanoribbons, where a lot of activity. In fact, our group is also working extensively on this. You can visit our lab's website to read a few papers here. All right, but this is how you would lay copper over an SiSiO2 wafer. So let us go one by one. If you see, let's say this is your silicon wafer, you make some trenches, then you put a thin barrier layer. What does this barrier layer will do? It will avoid copper from percolating inside the wafer. This is typically Ti or titanium, and it has a couple of advantages. First is that this titanium barrier layer provides a shielding for copper to and avoids it from going inside. It also provides very good adhesive strength for the metal lines which are pasted over the SiO2 dielectric. After this, you pour some copper over it, and then you polish it, etch it, and what you get are conducting lines, perfect conducting lines. Okay, but why do we use copper? I'll talk about it in a minute in the coming slides. Okay, type of interconnects could also be, as I said, based on their applications or their where they are put. So as I said, on-chip interconnects, multi-chip module interconnects, typically in case of motherboards, then PCB interconnects, then we have backplanes, and finally we have connectors, racks. As a matter of fact, the LAN cable is also an interconnect. This power cable is also an interconnect. So depending upon where you want to put it, you have various types or hierarchies of interconnects. Okay, now with this, I'm assuming that the audience has some idea of what these interconnects are, why they are important. Now comes an important question. How do I model them? To understand how to model them, we have to first understand what is modeling. Modeling is nothing but you are trying to develop an equivalent circuit of this wire which has some physical dimension, which is over a silicon SiO2 substrate or maybe over a PCB or something. Now, how do you extract the equivalent circuit? You have to calculate its per unit RLC. Now, you'll be surprised to know that all this data, this is very high-end research topic, but the motivation or the content lies in basic undergraduate studies. So all the material is available with us. We only need to brush up our fundamentals once again. If there is a wire, how do I find out the RLC of it? All right. So the first thing that we need to understand is, and that's very well explained in the previous slide, is whether the wire is electrically long or short. Because if it is electrically long or short, it will determine the type of equivalent circuit, whether the equivalent circuit is lumped or is it distributed. So that's the first thing that we all need to understand. And then we also need to understand whether they are local versus global, whether they are metallic versus non-metallic, on-chip versus chip-to-chip, so on and so forth. And my equivalent circuit would look something like this, which is on your left-hand side. So there are multiple wires which are connecting each other, and you have RLC, as you can see. Right? The remainder part of this presentation, I'll be focusing on how to compute these RLCs for a given arbitrary interconnect over a silicon this thing. So let us take the first component, and this is basically your capacitance. Let us say that this is your driver circuit, this is the load circuit, and there is a wire which is connecting this to this. It is offering an equivalent capacitance, and let me call it a C wire or CW. It is the interconnect capacitance. And the simplified model is somewhere here. There is a driver here, there might be a load here, and there is some CW capacitance available here. How do I compute it? So if there is a planar transmission line, a metallic line, which is running over SiO2, then the substrate is Si, doped silicon. You have a dielectric here, and then you have the wire over it. The wire provides the forward path for the current, while the dielectric, rather the substrate, provides the return path. That's how the circuit will be completed. And therefore, in all probabilities, we will have some overlap capacitance, and the overlap electric fields are shown here by these arrows. Now, overlap capacitance can be very easily, we can just brush up our 12th standard electrostatics fundamentals, and we can say that this is nothing but epsilon A by D, where A is the cross-sectional area of the wire. Now, let's say my wire has a width of W and height of H, right? And the length is L. Then I can use these parameters to find out the overall overlap that this wire is creating and calculate the first capacitive component, which is my overlap capacitance. I need to know the dielectric permittivity, and some of them are listed here. For example, typical SiO2 has permittivity of 3.9. Okay, that's the first part. That's fairly easy to do. But is this the only component that we have? If there is a metal line, there will be lines of field which will be actually coming from the edges also. And as we all know, again, basic electrostatics, these are called as fringing fields. So, which is, explained in these two figures A and B. So there are fringe fields coming out of it. Look, these are the overlap fields, while these are the fringe fields. All right. So how do I find out the fringe fields? There are standard expressions available to us, and I can use those expressions to find out the fringe capacitance. And if I look at these lines of field, what I can see is that the parallel plate lines of field are in parallel with the fringe lines. Therefore, parallel capacitance can be simply added up, which is shown here in the expression. So my total wire capacitance is nothing but C overlap or parallel plate plus my C fringe, and that is how I can find out my total capacitance which is offered by a wire. Of course, this was for a simplistic case, something like which is shown in figure A and B. In a real world scenario, which is shown here on the right bottom of the slide, we have multiple wires running over different layers, and therefore you will have parallel and fringe fields not only with the return path, you will have inter-wire capacitance also. So as you can see, let's say if this is line 1 and this is line 2, there is a parallel plate capacitance because of overlap of these two wires. There are fringe capacitances and there are lateral capacitances also. You need to add all these components together to find out the total capacitance offered by this wire. What we see here is an interesting phenomena, that if you look at this curve, we are moving basically towards the left hand side. That means we are scaling the technology. When we are scaling the technology, what we see is that our total wire capacitance is getting dominated by this inter-wire capacitance. The reason, of course, is as we are scaling the technology, devices are coming close to each other. Therefore, the wires are also coming close to each other. Therefore, inter-wire capacitance, or the ones that are shown here, something like this, these are more dominant compared to something like this, which are the parallel plate or overlap capacitance. Okay, so now I can calculate my capacitance. There are still two more terms to be calculated, and I'll quickly go through one by one. Let us now talk about the resistance. And this slide is nothing but the one that I was trying to say, that as we are scaling down, we see that the inter-wire capacitance here is contributing to the total capacitance. Okay, how do I find out resistance? Finding out resistance is very simple, very easy. Rho L by A is a standard formula which we all know. I know that my wire is made out of either aluminium or copper or silver or gold. Its resistivity is listed in this table here. Now, as I told you that the resistivity of copper is lesser than that of aluminium, and that was the motivational reason why people moved towards copper. As a matter of fact, silver is still more conductive, but there is a hardly 10% improvement, but the cost overhead is significant, and therefore people don't use silver. Plus there are fab issues involved, and therefore we are tempted to use copper. As a matter of fact, in today's world, copper is the industry standard material for on-chip or chip-to-chip interconnects. Alright, so I can find out my R for such an interconnect using its physical height, width and L, and I can find out R, right? Of course, the only difference here is that this is the DC resistance of the wire. Now this wire, if it is carrying power or ground, fine, this resistance is good enough. The moment it carries high frequency signals or clocks, I also need to find out the AC resistance. Now what is AC resistance? AC resistance is basically that the effective cross-sectional area reduces because of skin effect, right? And I'm sure most of us know what is skin effect. A skin effect basically means that the charge resides on the surface up to a particular depth, which is called as the skin depth. And that can be easily summarized by these standard expressions, and therefore I can find my frequency dependent resistance, or commonly known as the AC resistance, as R of F. So now I have R DC plus R AC, and that contributes my total capacity resistance of this interconnect line. The last is my inductance. Now finding inductance is a very complicated and tricky issue, whether it's a simple wire or solenoid which you roll around, or even these interconnects. Now what we can probably do here is we can use any of these three techniques and find out the effective inductance of the wire. So for example, I can say I can find out my L if I know my rate of change of current and my gradient of voltage. Now that's a tricky issue, because at times testing becomes an issue in such nanoscale interconnects. But I can use some other technique, which is basically C into L, which is, let's say, the per unit capacitance into the per unit inductance is nothing but mu into epsilon. And I can easily find out my mu and epsilon. And C I have just computed in the previous slide, so I can find out L. Alternatively, you can also find out inductance using any of these formulas, which are also available in standard electrostatic books, right? So the speed of propagation is nothing but 1 by root LC, where L is the inductance and C is the capacitance per unit length, which can be equated to speed of light upon mu r upon under root of mu r into epsilon r, and I can easily derive my mu r and epsilon r, and then C I have already computed, so I can find out my L. Of course, there is a word of caution here before you start using these formulas, that in these cases we are assuming, if I use any of these expressions, that I have uniform charge distribution. But as I've already told you, uniform charge distribution won't be there. So it's some kind of approximation is used here, but probably that's required given the complexity of your nanoscale interconnects. All right, now I'll come to the key performance metrics that define the performance of the wire. We talk about we talked about it earlier also. So delay is an important metric, energy dissipation is an important metric, bandwidth is a very important metric, and if you have closely packed wires, then noise or crosstalk becomes a major issue. And of course, losses, whether they are dielectric losses or metallic losses, both are of significant. Over and above this, this forms the part of your standard signal integrity problem. Okay, with this, I'll come to the last part of my presentation, where I'll just leave you with some couple of slides, which is just probing into what lies in future. And I want you to pay attention here to some of these things. This is one of the papers that I figured out, and what I found is an interesting curve. And the authors have compared, various families of processors, and they have figured out off-chip bandwidth in terms of terabits per second over the number of years. And what they have found is that in the days to come, we'll have thousands of pins, I/O pins, and each pin will be subjected to several tens of Gbps of frequency of data rates. Now that's an important thing, and this is very close. This is about in the next 5-10 years, right? So with such high data rates, probably if attenuation is a problem with metallic wires, we need to figure it out, what beyond metal wires. That's very important. Now, another thing that comes to our mind is this, that I need to keep my power dissipation constant, although my aggregate bandwidth has to increase because I need more and more functionalities. So that's a grand challenge that we have, and we look to actually not only keep the power dissipation or power efficiency constant, but actually reduce it. We want to go towards greener integrated circuits, which is also a major topic of the day, where people are working on on these topics. So what it means is that my bandwidth increases by almost 7 times or 700% in the next 5 to 10 years, but my power power dissipation should remain more or less the same. How do we do that? That requires intelligent wire performance and its optimization. So that's typically, and if I have typical data rates of something like a few hundred TBps and typical energy per bit as, let's say, as low as 1 picojoule per bit, then look at the power dissipation of the chip, 300 watts. That is way higher than your average ceiling fan. It's more than double than that. But look at the dimensions. So these are some of the topics where one has to work. Power scaling instead of device scaling is the order of the day. You have to talk about low power circuits and low power interconnects, and this is something where I'll request most of the audience to pay attention and maybe start exploring this as a possible research area. I'll summarize it, and in the summary what I would like to say is this, and which is basically highlighted in the bold, that to meet the next generational requirements of integrated circuits, you'll have a co-design of electrical and optical systems, particularly interconnects. That's one very important thing, and we have to give a lot of impetus to post-CMOS technologies like graphene-based technologies. Of course, this was more of an introductory class, and I couldn't really delve into these issues, but maybe some other time you can actually read a lot of the, these two things in our our ongoing research work in my lab. You can also read some of our papers, some of our recent papers which are available here, as well as these two books will give you a lot of idea about basic interconnect modeling and how to understand what is the meaning of a complex, rather a compact model, which is given in this book by Springer, and on 3D ICs and system, which is a more recent book which has been published only last year, and this is by CRC Press. Both of these are of course international editions, so you may find it a bit expensive, but you can definitely request your library to get a couple of copies. And a lot of problems are we have tried to address a lot of problems in in this literature. Okay, with this I wind up my presentation. I do have a small announcement to make, which is other than this presentation, is that to talk about some of these topics, we are actually conducting a one-day IEEE CPMT workshop in IIT Ropar, and this will be on the 7th of November. I'm not really sure how to make it a full screen though. Yeah, here it is. And this is called as the Advanced Semiconductor Packaging Workshop. It's on a Saturday, 7th of November. It's a one-day event. And the link is now available on our website, on the homepage of our website. It's sponsored by the IEEE CPMT Society. And if you have interest as a student or as a faculty member in attending the technical sessions, we have speakers from US. We have Professor Swaminathan, who's an IEEE fellow and a stalwart. He's a director of the Interconnect Packaging Center at Georgia Tech, who will be talking about the big picture about packaging industry, including interconnects. And then we have a person called Professor C. Balaji, who will be talking about the thermal and reliability issues in 3D packaging. We have people from industry, from Intel and Synopsys, and we have people who will be talking about computational tools. Professor Gope is there from ISC Bangalore. It's a one-day event. I would request the audience to go through the link, and if you find interesting, you might want to register for it. The last date, of course, is the 31st of October. We also have student poster sessions for masters or graduate students or PhD students rather. So you can present your work, and there is a best poster award also available. So I expect participation from you guys. We'll be talking about more details about what, of course, this presentation was more rudimentary or basic. Here we'll be talking about more advanced issues. Okay. With this, I wind up my presentation, and I thank the organizers once again for calling me here, and I'll be happy to answer your questions if you have any. Thank you. Any questions?
Yeah, hello sir. I am Yadvinder Gaurav from IIIT Gorakhpur.
Okay.
I want to know, can you give us some aspects on radiation hardening on vacuum-based semiconductor transistors?
Yeah, so red hard circuits are of great importance, especially for our defense application, particularly space applications. And what is important here is to understand that signal integrity completely changes the moment you have red hard circuits. Okay?
And performance in the noise performance and the
yes, it diminishes dramatically. As a matter of fact, I mean, coming back to the workshop once again, one of the speakers from Synopsys will be talking about signal and power integrity issues for such a scenario. His name is Rajkumar Nagpal, and he's a senior engineer at Synopsys. So, in case you find interesting, you might want to attend his session.
Good afternoon, sir.
Yes.
I'm from ABS Engineering College. I want to ask that inductor as a parasitic generates current bouncing. So how we can reduce that bouncing time?
So we can reduce the bouncing by minimizing the inductance. Of course, it's easier said than done, right? So here we were talking more about the how to calculate the RLC. How to optimize the RLC is a different ball game altogether. You can start with, there's a very good literature as a matter of fact. It's called Calculating Inductances. It's a very famous book by Grover, and that is where you can start understanding how these inductances play a role. You can also download a lot of papers, recent papers. Now, one way of reducing the inductance is that I somehow minimize its internal EMF, right? But that also is dependent on your material property. So can I go for a new material altogether? That's the big challenge. You understand?
Okay, sir. Could we make a change in the circuit for changing, reducing the inductance?
No, because change in circuit will not help you, because eventually the inductance is not offered by the circuit standalone, it's offered by the wire. You understand? It is affecting the performance of the circuit, because now you have ringings and oscillations, so you will have logic failures, and therefore I had mentioned there will be reliability issues. Okay? So once the logic changes because of inductance, my circuit will malperform. Okay? So you have to nip the evil in the bud itself. You have to tackle the inductance at the physical wire level itself, not beyond that, because beyond that it will become hopelessly difficult for controlling it. The cause of inductance is because there is a lot of internal EMF generated in the wire. How do you control it? Do we use a new material? Do we try to minimize the electrical lengths of the wire? Right? Because if I have electrically short wires, then I can say, bid goodbye to my inductances. But if I have more devices on the chip, then routing becomes an issue. You have to route wires which are long. The moment they are physically long, obviously their lengths, physical lengths will be greater than lambda by 10. So electrically also they may become long. It's a very complex thing. Calculating and controlling inductance of high-speed interconnects is one of the toughest topics to deal with. Okay?
Thank you, sir.
Further, any questions?
No, sir.
Yes.
Sir, HITM College, Agra, say.
Yes.
I think that you say that
Your
remove the copper.
Your voice is not audible. It's getting disrupted.
Aluminum by the copper.
Can you repeat the question, because I could not hear your question properly?
You say that aluminum is removed by the copper in the interconnection between silicon and silicon oxide interlayer.
Yes.
So, but copper is oxidizing problem.
No, there is no oxidation, my dear. The reason, of course, is the entire wafer is finally packaged into a hermetic sealed thing, right? You'll never find a naked die. It'll always be packed in that black color plastic packaging, isn't it? If you see a processor or a RAM or any other component for that matter, an integrated circuit is never exposed to the environment. So question of oxidation won't come here. Okay? Further, any questions? Thank you. Further, any questions? I think there are no questions, so thank you once again. Your voice is not audible. Can you please speak clearly and repeat your question? Can you please repeat your question? Okay, thank you. Thank you very much.
At JSS Noida, your mic is not on. Your external mic is off. You can just come near to the laptop and ask the question. It's okay. Or you can type in the chat window if you want to.
some messages there.
Or you can go to settings of Hangout and change your mic input. I think your mic input has been changed.
Would you like to pose any question?
So would you like to ask a question or not? Just wave your hand if you want to ask. ਹਾਂਜੀ क्वेश्चन पूछना ਤੁਸੀਂ ਉੱਥੇ ਟਾਈਪ ਕਰ ਦਿਓ टाइप here to ask
मैडम ने वेव किया है ना एंड क्वेश्चन तो पूछना चाह रहे हैं पर आ नहीं रही क्या प्रॉब्लम अपनी तो यहाँ से वॉइस जारी होगी
हेलो 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 यहाँ पर
इंडिया का फोन है
हाँ जी सर सर मैं बाजपन कर रहा हूँ यार मैं पास नहीं कर रहा हूँ
क्वेश्चन देख लिया यार
कॉलेज का नाम बता दें
JSS Noida, there is some technical issue at your end. Your voice is not coming. If you want to ask any question, then you just type your question in chat box. You can type your question in chat box.
chat box JSS का बोला not GDB.
How we can integrate this with antenna? And something else is also there. क्या first में क्या?
How we can integrate this with antenna?
One more query is there, I think, in first window. Just here.
So, I'm not really able to understand what your question is. How can we integrate this with antenna? I mean, can you elaborate what exactly do you want to ask?
So they might be working in antenna and they want to explore into this field also and they want to collaborate both things. Well, they want to know.
On the other hand, you know, you can also view my web page and my email is given there. You can contact me over email in case you have you know, further questions, because I believe there is a technical you know, disconnect here.
Hello sir.
Yes.
Yes, you are audible now.
Sir, I am Pawan Kumar from GDBIT sir.
Okay.
Sir, I am basically designing a mode for a wireless sensor network.
Okay.
Sir, can you tell me from where I get these facilities in India, sir? Fabrication facilities, sir.
So, for fabrication, I think, I believe you are trying to fabricate the sensors, right?
Yes, sir. Yes, sir.
And for fabricating sensors, the best thing is you can go to the INUP website, which is essentially the Indian Nanoelectronics Users Program, and there you can. So the INUP has come up with a lot of centers in various places. The most prominent ones are the Nano Center at IISc Bangalore and IIT Bombay. So they do work a lot of fabrication related stuff. They also conduct short-term and long-term courses. So you can register for these courses, visit that place, and you can get your stuff fabricated. Okay?
Thank you, sir. I got it.
Sir, उनका क्वेश्चन है टाइप, can you please highlight the features of high-speed interconnect?
So I think there is a question which basically says that can you please highlight the features of high-speed interconnects? I'm not entirely able to understand what you are trying to say here, but basically it was explained that the performance of the interconnect is basically dependent on some of its metrics, and these metrics include delay, how fast or slow the interconnect is, how noisy the interconnect is, therefore crosstalk. Then reliability becomes an issue, because once you have noise you can have logic failures, and that's an issue. And of course your power becomes a major issue, so you should have lower parasitics so that your overall conductor losses should be minimized for high frequencies. I think that is pretty much I can understand from this question.
Modeling changes in high speed interconnect.
not not able to understand what does it mean.
High speed interconnect में modeling change होती है.
Modeling.
So as I've already told you that modeling will depend upon whether the wires are electrically long or short. If they are electrically long, then you have distributed models. If they are electrically short, then they are lumped models. That's the basic thing. Of course, if they are metallic, then the models change versus non-metallic like carbon or optical. In that case, for example, in optical wire, there is nothing like RLC. The whole physics is of diffraction, of you know, how good the cladding is. So it's more on optics. So depending upon what is the operating frequency and the electrical length, as well as the material, your modeling changes. And 2D materials, of course, one of the most investigated 2D materials as of now is graphene and graphene based interconnects. So you can read a lot of things. Do visit our website. You can find a lot of papers available and you can read there. Okay.
Is there any more query from any nodal center? I think now there is no more query, and all queries are I think very much clarified by our expert. So it is time to thank our expert Dr. Rohit Sharma from IIT Ropar. He always help us, always cooperate with us, and whenever we invite him, he always give his valuable time to our institute, and he deliver his talk on his expertise area. And we are really thankful to Dr. Rohit Sharma for accepting our invitation and coming here to deliver expert talk on this high speed interconnects. And it was really nice presentation, and I hope all of you enjoyed it. And it was really very useful, and it is really very useful to work on your VLSI design. So once again, I thank Dr. Rohit Sharma for his talk on this topic. So I just here now I close this session, morning session here, and we can go ahead with our lunch part, and after lunch we will come again here, and we will start our after lunch session at 2:30, and our another expert is on his way, and he is from Cadre Design Systems, and he is going to talk about TCAD software, and that part will be based on software simulation kind of part. So we will be here at 2:30. So enjoy your lunch, and we will have break for lunch, and we will be here at 2:30 p.m. Thank you. Thank you very much.
Online.
तेरी मोहब्बत सही करो सब कुछ सही करो पांडे सर हिमांशु चयन करा गया है क्या? उसको कर दें? ऐसा होता है मैं भूल जाता हूँ फिर मेरे 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 आप कराओ तो अच्छा ना करो। चलो तो एक कपड़ा दिए थोड़ा कमाओ। ना है कपड़ा तो
ये रुको 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 वो है ना वो म्यूट करो
आप चेक कर लो सही है। हेलो हेलो
हाँ जी सर।
अभी
हाँ जी सर, हो गया सर वो।
किसने बता दिया आपको काम?
पैन नंबर लिखा
Good afternoon to everyone. Welcome to our third session on device modeling. This session will be delivered by Mr. Gaurav Musalgaonkar. Mr. Gaurav Musalgaonkar is a technical engineer in cadre design systems. He has a 1 year of experience in 3D TCAD modeling using Usual TCAD and Genius. He has done his MTech in VLSI from Thapar University. Now I request you, sir, to proceed this session.
Thank you. It is showing up.
Hello. 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 We are not able to hear. Hello. 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 We are not able to hear. Hello.
It is audible.
Hello.
Can I start? Well, this session is on your device modeling and device design. As we all know that if we can design our own device, if we can improve the parameters of our device, we can improve the circuit performance also. So my name is Gaurav. I am from cadre design system, and the tool for the device design is Visual TCAD. As you can see, this is the tool window. This is the GUI for the visual TCAD. You can see. So I will start from the very first device. 180 nanometer MOSFET. I'll show you how to design a MOSFET with our own parameters. As you can see, this is a 180 nanometer MOSFET device. This is a very basic conventional MOSFET. As you all know that the first MOSFET which were designed in the 1964, like this type of structure. In the 1964, we have a channel length. Channel length means this channel length about 20 nanometer or 20 micrometer. Right now we are having less than 7 nanometer of channel length. Now, how to design our own device? See, you can see this file option here. Then go to the new and device drawing. This type of window will appear. Now, for designing, you can measure the distance of one box. Okay. As you can measure the distance of one box. You can adjust this grid according to your device size. Suppose you are working on a 180 nanometer device, then you can adjust the size of one box according to that 180 nanometer. You can adjust 10 nanometer, 20 nanometer according to that. So by scrolling, you can adjust your grid size. Now you can see here it is 0.1 micrometer. Just a minute. Now, when I scroll, I can make the grid size according to my choice. See, now the grid size is 10 micrometer. Okay. Now to design a device, first of all we have to select a square. You can see this rectangle, add rectangle option. Go to the add rectangle. Then you can make a rectangle. This is your substrate for your device. Okay. This is your substrate contact. This is your drain contact. This is your source contact. You can make your gate oxide here. This is your gate oxide. And this is your gate contact. Now you can see the structure of your MOSFET, conventional MOSFET is done. Now you have to name the regions. For this, go to this option, click on this. Now give the region name.
Sir, your slide is not visualized, sir. Sir, your slide is not visualized.
Sir, can you say the slide name? You need to reload कर लीजिए.
You can use the F5 option. You can then see. Just reload your window. Now you can give the name of the region. Like this is a substrate base region. Base. Now you can choose the material, which type of material you want for your device. There is a lot of material here. You can go to the more and you can see for semiconductor we have so many of options available. Similarly for conductor also, for insulator. So right now I am making with silicon. So I am choosing silicon. This is silicon. Okay. Name is base. Okay. Now this substrate part is made up of with silicon. Okay. This is your substrate contact. Contact. This is of aluminium. We can take aluminium. Similarly, this is your drain, source contact. This is also of aluminium. Okay, 1 minute, 1 minute. Actually, this will not be white. This is only black.
अदरवाइज टेक्स्ट कलर को थोड़ा और कर सकते हैं व्हाइट ऊपर,
Uh,
जो ये हमारा लिखा हो ब्लू कलर में आ रहा है, इसको कर
okay.
सकते हैं.
Once I finish with this design, I will change the entire structure into more more hard colors. Okay.
You can go ahead and then.
So just give the name DRAIN drain electrode. This is also of aluminium. This is your gate material. You can either choose metal or polysilicon. I am choosing N polysilicon because we are making N MOSFET. And this is your oxide. Oxide. The material is oxide, SiO2. Once you give the name, then you have to do the doping. Okay. Now for doping, there are two options. You can do the ion implantation or you can do the simply diffusion. For ion implantation, go to this option. Now I am taking base as P-type dope. For this, click and choose the region. Then you can see that 4 type of doping option available: uniform doping, Gaussian type of doping, ERF doping, and database of type. So for substrate, we are taking uniform doping. Now again give the name base. Doping type is your acceptor type. This is acceptor type. You can take any concentration, whatever you want. I am just taking some random values. So you can see this is a P-type dope. Now the substrate is P-type dope. Okay. Now you have to make your source and drain region. For that, you have to take donor type of impurity. Again, this is Gaussian type. You can give the name source. The doping is little bit higher, 1E19. Type is donor. Okay, just okay. You can see this is your N type of doping. Similarly at the drain end. This is also Gaussian type. The name is drain. Drain. This is also 1E19. Okay. Now when you do the doping of source and drain, that one question is, if you see this structure, there are 2 types of doping. One is here LDD, if you know that, a lightly doped drain type of doping. Because what happens when we do the simple drain and source doping, for that you are doing ion implantation, then some impurity will appear into the channel, and that will make your device as a depletion type of device. And we do not want our device as a depletion type, because in the depletion it will there is a channel at 0 gate voltage also. So to make your device as a enhancement type, you have to make your threshold voltage implant. Okay, this is the threshold voltage implant. If you can see, there is a highly P type of doping just below the source and drain doping. See, this is your source drain doping, this is your source doping, this is your drain doping, and just below that we are making a threshold voltage implant. What will do this? See, some electrons are present just down the channel, so this highly P type of doping will neutralize those electrons, because electron and holes will get neutralized with each other. Okay, so for this we are doing this threshold voltage implant. Now when you done with your device structure and doping, see this is your complete structure, then you have to do the meshing. Now what is meshing? This is the option for meshing. See, this is the meshing. Now every TCAD tool work on the meshing principle. Meshing means for calculating the current, for calculating electric field, potential, everything, we require, the tool requires some points. Okay, so if you can see, there are some intersection point. These are cross some intersection point here. See, suppose this point. So every calculation will be done on this point only. Every TK tool works on your numerical methods only, like Newton-Raphson and different methods. So for iteration we require some points. So after doing meshing we get some points, and only on those points the calculation will be done. Okay. So when you do the doping and when you do the meshing, you can see your device. Go to the device, mesh 3D view. See, this is your device. Now you can see the depletion region here. This is your depletion region. You can see the junction depth. This is your junction depth. You can, if you can vary the doping of this region, the depletion region will also change. Okay. So this is your draw file, and in 2D only. When you draw your conventional MOSFET, then you have to save this as .drw file. Just go to the file and save as in some other folder. On desktop, new folder. Just save it as p18.drw. Draw is the extension. Okay. Now again, to use this file for simulation, you have to again save it as .tiff, tagged image format. Save as mesh to file. Again go to the same folder. Where is that meter? You can save it as a MOS 180.tiff. MOS 180.tiff. Save. Okay. Now this device is saved. Now for simulation, again go here, device simulation. Now this type of window will appear. Now open that file. This is your MOS 180. It will take some time. You can see the what is the progress here in console window. See, device is loading. It is running. Status is running. Okay. Now this is your device. Now device is loaded. Now in this tool, wherever you use metal, it will take it as electrode by default. Okay. Now you can see substrate. This is substrate. This is also aluminum. Drain also aluminum. Gate and your source. Gate, drain, substrate, and this is source. Okay. Now there are three options: boundary condition, your physical model, and solver option. Now what is physical model and what is boundary condition? See, sometime if you know the inverter, in inverter we are shorting the substrate and source terminal. Okay, by using this option, go to the interconnect, you can short two terminals. You can see that here, source and substrate. Source and substrate. I can short this two terminal, and you can give some new other name like SUB. Okay, you can see that source and substrate are shorted here. Now you can change the work function of your material also. If you are using polysilicon, aluminum, whatever, tungsten, any material, you just can change the work function of your material by changing this value. You can see this for gate, by default the work function is 4.17. You can vary this value also. I am taking by default value. Now in this option we are having model definition. Now what is model? You all know now we are not using 180 nanometer device, we are having 22 nanometer or below 22 nanometer. Now at such a
smaller dimension, we are having so many effects like quantum effects, because electron can behave as a particle as well as can behave as a wave. Now in both the cases, we are having different equations for your current and all other parameters. Now you can see there are three types of equation: basic drift diffusion equation with lattice heating, and energy balance drift diffusion equation. Now basic equation is applicable where when the channel length is much higher, 180 nanometer or more than 180 nanometer. When you want to see the effect of temperature, then you can use this second equation, drift diffusion equation with lattice heating. And when you want to see the effect of quantum tunneling, quantum phenomena, then you can use this energy balance equation. Okay. Now again change the properties of your material also. See, in the silicon region, where this is silicon, there are so many models like band to band, impact, mobility, optical, thermal, and trap. You can use the band to band tunneling model, you can use impact ionization model, mobility model, optical model, thermal, any kind of model. Whatever technology you are using, working, you can include that model. Okay. Now once you apply all the model, once you use the boundary condition, then you have to bias your device. See, I am giving 0 to 1 at gate with a step of 0.05 and at drain 0.1 volt. Substrate is at 0. Substrate at is 0. Okay. Now just save this simulation. In the same folder, give name at MOS 180. Extension is .sim. Now save it. And now run it in the same folder. NITTTRCHD. Okay. Now it starts running. You can again see the progress in this console window. It is running. And you can see the result here. It is ramping your drain voltage up to 0.1 and then it starts ramping your gate voltage. .15, 0.25 up to 1 volt, 0.3, 0.35. Now select all this, then right click and open spreadsheet. Now all the result will appear in the spreadsheet form. Now if you want to see the drain current versus gate voltage, this is your drain current and this is your gate voltage. This is your IDVG curve. Just a minute. You can see this is the IDVG curve. Your simple. Just refresh this. Refresh the. This is your IDVG curve. Okay. Now you can change the plot. You can make any type of. If you want to see this into the logarithmic scale, this is your logarithmic scale. Okay. You can see here that threshold voltage is around 0.2 or 0.3 in the linear. The threshold voltage is around 0.3 or 0.4 volt. Up to 0.3, 0.35, the gate current is 0 and then it starts increasing. Okay. Now one more thing. You can visualize all the results. Again select this, right click and open visualization. Now see, if you want to see the electron current, how electrons are generated, just go here. Just a minute, I just close this. Now see electron density. You can see the electron density. At source and drain, we are having the maximum number of electrons. This is your p-type of region, substrate. In p-type, we are not having electrons. In only source and drain, we are having electrons. Now, if you want to see how the channel is created, how the electron starts created, so you can go to this electron current. Now see. One minute, net charge. This is your net charge. What is so? See, 1 minute. This is your n type of doping. This is bulk is your doped with P type of doping, P impurity. You can see the value 1E18. Similarly, the N type of doping, ND. This is your source and drain doping. Okay. Now see 0. Just minute. Net doping. This is your net doping. This is your drain. Now you can see that there is no electron in the channel. Here only P type of doping. Now I start this. Now you can see that channel will created here. If you can see this in the logarithmic, you can visualize this. Similarly, this is your electric field. Everything you can see here. Also, the see potential, electron density, hole density, your net doping, net charge. If you are using a compound material, then you can see the mole function. And these are some physical terms, recombination like Auger recombination, your SRH recombination. Similarly, the conduction band energy, valence band energy, Fermi potential. You can see all those things in this window. Okay. Now this is your conventional MOSFET because only one gate is present here. But right now we are working with a 7 nanometer up to 7 nanometer technology. This is 180 nanometer channel length. Now as we reduces our channel length, we have to change the dimension, we have to change the device also. Now you can see in this PPT, this is a double gate type of structure. As you can see, there are two gates. One is here, one is here. Okay. Similarly, this is your tri-gate structure because we are having three gates here. One here, and one more here. Similarly, there are few more advanced structures like this. This is the conventional FinFET structure, SOI FinFET. This is your source terminal, this is your drain terminal, and this is your gate. Like one more structure is there. This is your structure with spacer because at a very lower dimension we are having the heating issue. So for reducing that heating issue, we have to use this nitride spacer to cool down the device. And the very latest structure is this nanowire because we are having the gate on all four sides. This is your cylindrical nanowire. You can make in a rectangular form, triangular form, any form. This is your cylindrical nanowire. So how to design this type of structure? Basically, these all are very advanced structures. This is the very basic structure, 180 nanometer. See, this is your double gate structure with four spacers. Similarly drawn in this 2D window only, you can see this is your substrate base, this is your drain terminal, this is your source terminal, and this is your gate oxide at the top, and this is your top gate, this is your bottom gate, this is your bottom gate oxide. Okay. Previously we are having only one gate at the top. Now we are having two gates, one at the top, one at the bottom. Similarly, FinFET. This is your conventional FinFET. You can see all three sides. This one side, top, and now this right side. We are having all three sides a gate, and channel will form in only if you remove this oxide, this is your complete substrate part. If you see the doping, I think doping is not here present. If you see, this is your source part, this is your drain part, and this is your channel part, complete channel part. Now the dimension, you can see this dimension are very small, 30 nanometer, 22 nanometer. Previously we are having 180 nanometer. That's why we are having only one gate. But now to control the gate current, we require three. To control the channel current, we require 3 gates. Similarly, one more advanced structure. Just a minute. So this is gate. This is the structure I want to show you. You can see complete. The channel is similar to the tri-gate only, but now we are having the gate on all 4 sides. Okay. Now how to design these structures? For this, there are 2 methods. Either you can use your layout to design your structure. If you have the layout of your, see, if you are using more than 10-20 devices, you can use your layout method. You just design your layout, and then using one of our tool, you can create device. But if there is only one device or 2 device, you can use the deck method. You can write the deck file. See how to write the deck file for 3D structures, advanced structures. If you take an example of tri-gate, this is the tri-gate, this is the input file. See, this is the input file for this structure. This is the tri-gate structure. You can see, if I remove this aluminum and oxide and aluminum part, you can see the gate is present on all 3 sides. This is your source electrode, aluminum. This is your source aluminum. This is your drain electrode, and this complete silicon bar is your complete channel. This is the source doping, this is channel doping, and this is drain doping. Now see the code for this structure. The code can be written in 5 different steps. First of all, you have to define the coordinates, from which point to which point, which kind of material you want to use. Then you have to fill the material, then you have to do the doping, and then apply the biasing. Okay. Now see the code for this structure. You can see here we are having the x axis. This is your x axis, 0 to 420 nanometer. Okay. Now you can see here from 0, the initial starting point for all the axis is 0. From 0 to 1 nanometer or say 5 nanometer, we are having that source electrode. Okay. Now from 5 nanometer to 105 nanometer, we are having our source region. Again from 105 to 315, we are having our channel region, and then 315 to 415, we are having drain, and again the electrode region. Similarly on your y-axis and your z-axis, you can see the code. Now the x initial starting point is your 0. Now from 0 to 1, we are having your source electrode, this line. Again from 1 to 8, we are having our source region. Then I have given that 1 and 1. Now what is this 1 and 1? If you see the meshing, if I remove this, you can see that meshing here is very dense. Okay. Now you all know that the doping of source and channel is different. If you are using your, if you are making your MOSFET, any BJT, anything, the source doping or your, you can say, base collector doping is different. Now whenever there is a difference in the doping, there will be some junction form. Okay. And if you know, the every losses, every leakage current will occur only at the junction. So that's why I already told you that all the calculation will be done on the points provided by this type of meshing. Okay. Now we know that losses are more at the junctions. That's why we require more point at the junction. Okay, that's why we are giving very dense meshing at the junctions, because the concentration of your source and channel is different. Similarly, channel and drain is different. That's why wherever the junction is formed, we are giving meshing little dense. That's why what I am doing is I am giving just 1 nanometer from here to here, and from here to here 1 nanometer, and in that 1 nanometer region I am doing highly dense mesh. See, this 1 nanometer is your for aluminium, this 8 nanometer is for your source, and this 1 nanometer and this 1 nanometer is for your that highly dense type of region. This is your highly dense meshing. You can see that in 1 nanometer we are having only 1 spacing. In 8 we are having only 4 spacing, but in this 1 nanometer region we are having 5 spacing, means more number of meshes. Okay. Now similarly, this is the 20 nanometer for channel region. This is your channel. This region is your channel region. You can see the net doping. No, there is no doping. No. If I show you the material, now you can see this is your source, this is your channel region, this is your drain region. Okay. If you like this, you can see that red is drain region, green is your middle silicon, means channel region, and blue is your source region. Okay. Now similarly, when you define the x-axis for aluminum, for source, for highly dense mesh, this is for channel, again this is for meshing, and this is for drain side, and this is for drain electrode. Similarly, you have to define your y-axis and z-axis. Once you define your meshing on all x, y, z direction, then you have to fill the material in that region. Means if you define your source region from 0 to suppose 10, similarly here 0 to 10, and on z axis also 0 to 10, then only on those coordinates you have to fill your material. Like here you can see, first we fill complete region with the oxide region. Label we give as n spacer, material is oxide. From where to where? X minimum 0 to x minimum for x maximum 42, because the maximum value of x axis is 420 nanometer. Similarly, y 0 to 14 and z 0 to 12. This is the maximum dimension. I just fill complete with oxide only. Okay. Similarly, then when I fill complete oxide, then I start to etching, because this is the process when we use in the fabrication. So you can see 0 to 1 is your aluminium. Sorry, 10 to 32 is your aluminium. This is your gate region. See this point. From here to here is your gate. Material is aluminium. Similarly on y-axis, when you give the material, then the third step is do the doping. Here you decide the material, what kind of material you want to fill in your device. Then you have to dope that material. Here we use uniform doping in all the region, in source, drain, and your substrate region. See, this is your source and this is your drain, doped with n type of donor material. Concentration is 1E20. From where to where we just give the coordinate according to the device dimension. Similarly, this is your substrate region. The doping type is acceptor. Okay. Now when you do the doping, then third step is you can define the work function, what kind of material you are using as a gate electrode. For this we have to give the physical model interface, PMI. The region is gate. This is the electron affinity. See, every material composed of few properties only, like dielectric constant, electron affinity, its Fermi energy, valence band energy, all this. You just define that properties of that material and you can use any material. So I am giving 4.4 as a work function for this gate material. So now if you want to use any model, like if you want to use a mobility model, Lombardi model, like if you want to use your quantum model, you can give the definition of those model here only. Now when you give the model definition, then you have to do the biasing. Only we have drain, we are doing DC, we are giving DC voltage because we have to find the threshold voltage. That's why we are doing DC characteristics. So just define the drain voltage, label ID is VD, For gate we have V gate, and for source and substrate we are having only ground, because source and substrate is a 0. Now similarly in the device we are using Poisson's equation. If we are using simply drift diffusion type of methods, if your current is due to the drift and diffusion method, then you have to use the Poisson's method. If you are using your current conduction is due to the quantum method, then you have to use different type of method. This is complete physics only. When you define your solving method, then you have to export your output file. This is the command for exporting your output. Export what type of file? CGNS file. You can give any name, and extension is .cgns and .vtu. After exporting, you just here you define the electrode, but not attached. Here you can attach those electrode to your source drain and substrate region. See, electrode name is N drain and ID is VD. Similarly, we are using Newton-Raphson's method. Already I told you that all the device simulator working on only on your numerical methods. Method name is Newton-Raphson method, and here I attach the gate electrode. Okay, and this is your out file gate underscore IV. Now when you write this code, you just have to save this, save as whatever name, and the extension is .inp. Okay, once you save this, you just have to run it. Go to the tool and run as Genius deck. This is deck file or inp file. Okay, when you start running, you can see the progress in your console window. You can see that this is connected and starts running, but it will take time. That's why I am stopping it. This is the very basic structure, simple tri-gate structure. Simple tri-gate structure. Now there are so many advanced structures, like one more structure I want to show you. That just a minute. See this structure. See, this is SOI type of FinFET. Here what we are using is spacer material. I already told you that when you are using your device is very small dimension, like 22 nanometer or below 22 nanometer, then there are several heating issues, because at such a small dimension there is no space for heat to out. That's why we are using spacer. Now you can see that this is a source and drain electrode. This is your gate material, poly. This is your gate material. This is your gate oxide. Gate oxide. This is your buried oxide. If you know what is SOI, this is your buried oxide. The code for writing this type of structure is also the same. You can write your deck file according to your coordinates only. Okay. One more advanced structure is the very recent structure is gate all around structure. This is gate all around. It will take just 10 seconds to open. Just a minute. Just a minute. See one more structure. This is using layout method. See, if I remove this SiO2, these all are very advanced structures, aluminum. Now you can see here the gate is covered with from all four sides. This is triangular type of gate all around structures. If you see the doping, net doping, see, this is your source, this is your drain, and this is your complete is gate material. But here the gate is covered from all four sides. Previously in the 180 nanometer we are having only one gate, but here the from all four sides we are covered with the gate. So this is a your advanced structure created using layout. Then how to use layout? There is one more tool, inbuilt tool. See, this is your K layout. This is the inbuilt tool in the Cogenda. You just have to make your layout, and with the layout you can create any type of structures. This is the layout. I'm just showing you one NMOS layout and then how to create a device using layout. Open. See, just inverter. This is the layout of your inverter. Okay. Now if you want to make the device of this inverter, how the device will look like, just open GDS to mesh. See, this is the window for creating your device from the layout. For that you have to use a process file and your layout. This mask file means your layout file, and this is your Python process file. Now I am creating one structure using layout. Just take one layout. A trapezoidal type of FinFET. Okay, this is your Python file. We just select the FinFET process, and then this is the mask. Now you can see the layout in this window only. Just create mask. Okay, okay. See, this is the layout of that trapezoidal FinFET. You know the layout, simple NMOS type of layout. This is your source region, this is your drain, and this is your poly. This is your substrate contact, this is your poly contact. Now generate the mesh from layout. You can give the name in the same folder. Where is that NITTTR demo? Give the name as FinFET. Open, and starts creating your device from the layout. You can see the progress here. Once it finished, you can see your device, how the device look like. The total, these all are meshing points, total number of points, on how which number of points it will calculate the results. Total number of points is 52,200. I'll show you one structure of SRAM using layout. See, this is the SRAM structure. If I remove this oxide, you can see the SRAM. This is W and aluminum contacts. Now this is 6 transistor SRAM. You can see that 1, 2, 3, 4, 5 and 6 transistor SRAM. You can see the doping also. These all are generated using layout only. Okay. See, this is your NA type of doping. This is your donor doping. This is your net doping. These are generated using only layout. The layout for that SRAM is this is the layout. You can see the 6 transistor here. 1, 2, 3, 4, 5 and 6. As the layout is, the device will also look like the same as your layout only. This is the device. But now you can use, this is the actual virtual device. When your device will fabricate it, the device will look like the same only. You can do the simulation before fabricating your device here only, so that you can see the result, how will your device will work after fabrication. So this tool will provide you you can see before your fabrication that what is the output for your device. I think that trapezoidal FinFET simulation is completed. Now it is completed. Now you can see that trapezoidal FinFET. At below 22 nanometer, we are not having the exact rectangular shape of our device. We are having some trapezoidal type of shape. In the NITTTR demo, FinFET is 3D. This is your trapezoidal FinFET. I just remove this CO2. W also. Now you can see the fin shape is not perfect rectangular. This is due to the limitations of the lithography. Up to 22 nanometer we are having exact rectangular shape, but after 22 nanometer we are not having exact rectangular shape. We are having shape like some trapezoid. If I remove this substrate and this part also, now you can see your channel is not perfect rectangular. This is type of some rectangular shape. This is below 22 nanometer. You are having this type of structures. You can see the doping also. This is your Na. If I remove this, gate oxide material is HFO2 here, high K material. Up to when we reach up to 22 or 45 nanometer, we have to change the gate oxide material due to the gate leakage. So here we use HFO2 as a gate material. So these all are structures made using layout method, GDS to mesh method. This is your trapezoidal FinFET. One more structure that I want to show is see one more type of FinFET, SOI FinFET. This is SOI FinFET, but this is not conventional FinFET. If I remove this oxide, you can see the fins are extended here. You can see the doping also. Na. The doping in the channel region is extended from the source to channel. This is undoped part. Why we are doing this? To reduce the random dopant fluctuation. There is a phenomenon called random dopant fluctuation, because as we reduce the dimensions of our device, we have to make the doping high according to the scaling rules. So when you increase the doping of your device, then some random dopant fluctuations problem will arises. So to reduce that problem, we have to make our fin little bit extended from the channel. So the channel is only this part is your channel, but your fin extended from this point to this point, this point to this point. So this is one of the latest structures used in the device fabrication industry. But you can, one more drawback of this structure is, as you make this part as intrinsic to reduce the random dopant fluctuation, the resistance of this bar increases. So now how to reduce that resistance? For this we have to use some spacers, nitride spacer or some high K material spacers. So there are so many papers on this type of structures, and so many people are doing the research on this type of structure. So these structures are also possible in this Cogenda, and these all are also designed using only DAC file. You see the DAC file, very small FinFET saturation. This is the DAC file for this structure. The similar the DAC file, first we have to define the coordinates, then we have to do the doping, define the material in that those coordinates in those part, then we have to do the doping, and then biasing. Okay. Now one more thing, suppose you know the ultimately we have to make a circuit. So once you design your device, you can apply those devices into your circuit also, because if the performance of your device is improved, your circuit performance will automatically improve. Now for this you can see that circuit schematic. Okay, once you design your device, like I take one example, device drawing explorer example, again the same MOSFET structure. Suppose this is your device, you design according to your dimension, doping, everything, you do the meshing, everything you do, you save it as mesh to file in some folder like MOS 180, save. Yes. Okay. Now again go to the simulation. Open that MOS 180. Now instead of doing the simulation, you can make symbol of your device, and then you can use those symbol into your circuit. Now see from here, circuit element. You can see this. You can change the symbol also. You can take any MOSFET type of structure and MOS. Okay. You define the pins, like this is source, this is gate, this is your drain, and this is your substrate. Now this symbol will have all the properties of your device, not your, like the model file. Suppose the threshold voltage you want 0.2, then design your device according to that particular doping, particular values, and you can have that particular device. Now you can use this device in your circuit also. Okay, you can make like oscillator, SRAM, whatever you want, you can make. Now simply save this, give the name as NMOS, and save. Now for using this, just go here, circuit simulation, sorry, circuit schematic. Now this is the similar SPICE window. Okay, here we are having so many components by default. You can have all the components like capacitor, inductor, resistance, all the different BJTs, MOSFET, connector, everything we are having. By default we are having all the elements here. And for your element that you have created, go here. This is your nmos.sim. This is your device. Okay. Now the properties of this device and the by default present here, both are different. Now similarly you can make, if you want to make your inverter or whatever, you can make simply resistive type of inverter or NMOS, PMOS type of inverter. Just do the biasing, complete the circuit, and do the simulation. I will give you one example. See, this is the inverter. This is the inverter schematic. This is the inverter schematic. Now there is two way. If you want inverter, you can make in the device drawing window also. See, this is your NMOS. This is your NMOS. Just separate this NMOS with an SiO2 and define and make one PMOS, and then short the gate terminal. See, I have one example for that. Explorer. inverter. It is running, it is loading. See, this is your structure. This is NMOS. I just make another PMOS here and separate both the NMOS and PMOS with an SiO2. So now you can short the source and substrate terminal using this boundary condition. You have all the terminal here like AND drain, AND gate, AND source, AND sub, P drain, everything. Now just use interconnect, and whatever is the configuration for your inverter, your PMOS drain and PMOS source and your substrate is shorted. Similarly, and drain and substrate is shorted, and in NMOS your source and substrate is shorted. You just short those terminal, and you can simulate, and the characteristic will be same as your inverter only. So you can design 1, 2, 3, 500 any number of transistor in the 2D also, but sometimes designing in 2D is very difficult. That's why we prefer the layout method, which I already shown you. See the layout of SRAM. This is the SRAM layout. If you have a layout of your 6 transistor SRAM, any oscillator layout, whatever kind of layout, you just make layout, and with this layout we will create a device using GDS to mesh method. This is simple your NMOS structure, but the process we write for trapezoidal FinFET. That's why the structure will look like a trapezoidal FinFET. Okay, I will show you one more structure using layout method. One minute, just open. Now we will create a layout NMOS using layout method. Under GDS to mesh examples NMOS 130. It starts once it create, will show the results. See, 1 minute. See, this is your conventional, one more example of double gate structure. This is your conventional double gate structure, because here we are not using the your, you can say, extended fin method. This is our conventional, because from source to drain we are completely having the gate, but in the advanced structure we are having extended fin, like in this type of double gate MOSFET. One minute, this is not that. Monitor demo. This is double gate extended fin. This is the structure. Now you can see the gate is only at the center and the fins are extended, but here the gate is completely from source to drain. Now if you simulate both the structure, you will have different characteristics. Why? Because in this structure the gate off current, because in device we have to improve only 4 parameters like DIBL, subthreshold slope, I off by ion by I off, and threshold voltage. Now in this structure we are having less off current. Why? Because the region here, this is of intrinsic type. The doping at here at this region is very less, but in this structure we are having completely doped structure. Substrate is completely doped. So for current to move from source to drain, for electron to move from source to drain, the resistance is higher. That's why the off current is less. Okay. So this is the new structure to reduce the off current. So if you make an inverter using this type of structure, you will have less leakage as compared to the conventional MOSFET. Show you. Just a second, it is opening because the 3D file for this gate all around is very heavy, around 500 MB. That's why it is taking time. You can see the progress. It will open in just a second. I just close this. This type of structure I want to show you because this is the advanced structures. Now in India, everybody is working on this type of structure, gate all around, because the leakage in this structure is very less because we are using gate from all four sides. Now it is opening. See, you can see the structure. If I remove the SiO2 on left, so basically what I want to tell you, to create this type of structure in Cogenda is very easy. If you compare with other tools, the code for this structure is only 25 lines. If I show you the code, gate all around, this is the input file for this code. This is very simple input file. Why? Because see, basically we are having different types of mesh. If you are using a structure like rectangular, then you have to use rectangular type of mesh. If you are having some trapezoidal FinFET, then you have to use that type of mesh. So we are having the circular mesh for this type of structure. You can see that here we are using cylindrical 3D mesh. Mesh type is cylindrical 3D. Okay, this is by default temperature is 300 degree Kelvin, and the mesh type is cylindrical 3D. If you see the mesh of this structure, mesh is cylindrical. Just a minute. See, very dense meshing. Because the dimension of this type of structure is 5 nanometer. The radius is 5 nanometer. That's why to calculate all the points we require very high meshing. Okay. Now see the code. Because this is a circular structure, that's why we have to define the radius here. Once you define the radius, you can see that small circles are here. Okay. Small circle and that are extended. First we take some small circle, then suppose first we take 1 nanometer radius circle, then 5 nanometer, 10 nanometer. In this way we refine our structures. See, from 0 to 0.5, then 0.5 to 2, 2 to 25, 25 to 60, 80 to 90, 90 to 100. Okay, so there are layers of circles and we divide this circle into 12 equal parts. If I zoom this, you will be able to see this center part will be divided into 12 and then it extends. See how to write the code. First we have to define the mesh for nanowire. R mesh, radius of the mesh is 0 to 0.5. Now what is the meaning of the 0 to 0.5? 0 to 0.5 it will make a cylinder. Okay, then you can fill any material in that particular region. 0 to 0.5 you can fill any material. Similarly 0.5 to 2 it will again make a cylinder from 0 to 0.5 to 2 radius. Again you can fill any material in this region. Similarly, how many number of region you want, you just divide according to that particular region. So because in cylindrical mesh you can see we are having silicon, then we are having SiO2 and then we are having aluminium. Okay, so according to the requirement what type of structure is we want to design, you have to design your meshing. See, this is the material. You can see inside this SiO2 complete is silicon, then above silicon we have SiO2 and then aluminium. So according to our requirement, if we want to refine our structures, we have to just give according to that this dimensions. Once you give the dimension, once you define the meshing, then see z-axis is same according to your 3D structures. From 0 to 1 we are having your source electrode, then from 1 to whatever be the dimension you have to define your source part, then channel part, then drain part, and then drain electrode. And this is your channel electrode, gate electrode. Okay, now 0 to 10 we are having that source part, source electrode. Then from 10 to 70 we are having source region. From 70 to 250 we are having our channel part, channel region. Similarly, the 250 to 310 we are having drain part, and then drain electrode. Okay. Now once you define your dimensions, then fill the material similar to that 3D code only. From 0 to 100, first I completely fill with aluminum 0 to 100 because the maximum radius is 100. 0 to 100. First I fill with complete with aluminum only. From where to where? 0 to 320 maximum. Okay. Then from 0 to 90, then I start to etching. 0 to 90 I fill with SiO2. 0 to 90 in three different regions. 0 to 70, then 70 to 250, then 250 to 320. You can take your own dimension, that is no problem. This is this type of, if you want from 0 to 320, you can take in one line only. Okay. Then when you define your SiO2, then define your silicon. Silicon in only in the channel region. The channel region in your source and drain region. So 0 to 80, 0 to 80 is your radius of your silicon region. Then Z dimension 0 to 70, 70 to 250, 250 to 320. And every time you have to refine your theta. Complete theta is 360 degree. Okay, complete cylindrical is 360 degree. So once you define your meshing, then your material, then you have to do the doping, and then you have to do the biasing. I just remove this part. This is your doping. What type of doping you want? Donor, acceptor, P type of, N type of, and then you have to do the, you have to apply the method, Poisson's method similarly, and then do the biasing and export your structure. So in this way you can define your gate all around structure or any advanced structures as I shown you in this device. This is one of the advanced structures. These all are very advanced structures because right now research is going on only on this 3D structures, Tri-gate FinFET structures. There are so many different structures for FinFET also. Basically 5 types of FinFET structures are available in the literature, but if you are able to change and if you can improve the performance of your device, then it will be a very good work. See, one more thing I want to show, how to use the models, because right now research is going around 22 nanometer. So,
hello, 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 NITTTR.
Yes.
Sir, can you show the results of these structures? Do you
Yes.
have some parameters, simulation parameter?
Yes, sure. Now see, this is the simple 22 nanometer. I just want to show you. Video. 1 minute. First, I have to show you the structure. See, this is a one kind of structure, double gate structure. Okay. I will show you the result of these structures. This is the structure. Okay. Here what I am doing is the oxide is replaced with high K material HFO2. Why? Because the dimension you can see 24 nanometer only. Okay. Now at this dimension the oxide thickness is around 1 nanometer only. So 1 nanometer, what happens? The electrons penetrate through the gate material, and you all know that gate current for the MOSFET is 0. We have to make that 0 gate current. But if we have 1 nanometer oxide, then the electron will penetrate that 1 nanometer. That's why we have to use high K material. Now I want to show you the results. See, this is the 24 nanometer. If I show you the data file, result.dat. See, this is the result for HFO2. Drain current versus gate voltage. Drain pad versus gate voltage. This is our IDVG without quantum model. Okay. Now I am applying the quantum model. If you can, I will show you the file also. 24 nanometer. This is the input file for the quantum model. Okay. See, this is your 2D structure, struct.cgns. Okay. This is your definition of your electrode and everything. Now here I use the quantum model. This is the definition for quantum model. This is the definition for quantum model. Okay. Up to here. What is means basically every model is some sort of parameter list, and they have changed the value of parameter. If you are using Lombardi model, then according to the Lombardi model, what is means the mobility value of electron at the surface is different as compared to the bulk. So when we are moving to the shorter dimensions, then some parameter value changes. So those changes are included in the model definition.
Excuse
So
me,
this,
can't we give the this boundary condition externally?
yeah, definitely. See, in this window, you can go to the boundary condition. Whatever your structures, just go to the boundary condition.
Basically, the boundary condition.
Yeah. See, if you want to add any model, you can add model here only. See, this is the material model definition. Suppose you want to add a model in the semiconductor region. Okay. Now here we are having all the options. Suppose you are using mobility model. We are having all the 5 model: analytical, constant, high performance, Lombardi, Lucent, and Phillips. Basically, the maximum people use Lombardi model because this is more correct. So in the substrate region, I am using Lombardi model. But if you want to add your quantum effects, then you have to write the DAC file, and then in that DAC file, you can include the model. So when you include some basic model, you just go to the simulation and write the DAC file. In any folder, you just save it. In the NITTTR demo, I save it. Okay. Now you can open that file. This is your DAC file for that structure. This is the DAC file for this structure. Okay. This is the DAC file. Now in this DAC file, we are having only one model definition because we apply only one model. You can see this physical model interface command for applying any model. Okay. Now after this model, you can apply any model. If you want to apply your quantum model, if you want to apply any other model, you just give the definition of that model. And for all the model, we are having the documentation here only. In the visual ticket, physics in the Genius device, you can see for every model definition is given in the this help document. Okay. Now when you give the definition of your model, just save it and run it as Genius deck. I am not running. Why? Because it will take more than 2 and 3 hours. The quantum model is very time consuming. It will take more time. That's why I am not running this. But I have all the results. See, I'll show you the one result without quantum model and with quantum model. See, this is the result without quantum model. Okay. Now see the drain current versus ID, gate voltage. This is your without quantum model. Okay. Now I am showing you result with quantum model. This is the quantum model, including quantum model. Again, I am drawing that drain current versus gate voltage. If I just, there is the drain current. Control C. Now see the difference with quantum model. This is with quantum model. I just rename it with underscore quantum. Okay. Now you can see the difference with quantum model and without quantum model. If you take the logarithmic, with quantum model and without quantum model. This is your quantum with quantum, and this is without quantum. Similarly, you can apply any model and can see the result. Here only you can give the definition of your model only using this physical model window. You can give the material model as well as physical model. Okay, now see, if there is a base semiconductor region, you can use impact ionization. If you want to see the gate current, gate leakage current, then you have to use carrier trapping or your tunneling model. Okay, band to band tunneling, FN tunneling, direct tunneling, what type of model you want to use, and the definition for all the model is can be taken from this help manual. Okay, you can use the Fermi direct function, Boltzmann function. This is the your energy balance equation. You can use, this is physical model, this is material model, and global parameter can be defined here only. If you want simple basic drift diffusion equation, you can use DDML1 basic drift diffusion equation. If you want to see the effect of temperature, how the current will change with the temperature, then you have to use DDML2, that is drift diffusion with lattice heating effect. And this is your hydrodynamic model, that is your quantum degradation model. You can define the temperature here, everything. In boundary condition, this is your boundary condition window. Suppose if you want to give some resistance to your drain terminal, you can make simple NMOS, and then if you want to attach a resistance to that drain terminal, you can do here only. See, this is your drain terminal, drain pad. You can give the value to the resistance. Whatever you want to attach, you can attach here only, and then you can do the simulation. Okay. So this is the main thing. In 2D, you can make your device, then you can save it as a symbol, and then you can use as a circuit, whatever. Similarly, 3D, there are two methods that I have shown you. That one is writing a DAC file, and if the circuit is very complex, then you can use your layout method, that is GDS to mesh method. Okay, but for single device, two device, you can use simply your GDS writing a DAC file, INP method.
So in 3D structures,
yes,
can have an option for movable structures, more somewhat similar to the MEMS structures.
Sorry, repeat once again.
Can we design some movable structures, mechanical structures, I mean, for MEMS purpose for lower dimensions in the range of micrometer or
yeah, in micrometer we are already doing one project of silicon detectors.
Okay.
That silicon detector, the dimension for the silicon detector is 300 microns. And what is the main purpose of that detector is when we are doing some alpha beta particle bombarding on that silicon detector, and then we are finding that how many number of electrons and hole pairs are generating inside that diode. Basically that structures are radiation hardened. That means what ICs are used in the space, that type of structures we are designing. I can show you one structure. Right now I am not having that structure.
No, my question is, this is about the VLSI you are talking about. I'm
Yeah.
talking in terms of the MEMS.
See, in MEMS I don't think that we are supporting the MEMS, because in MEMS means what kind of structure you want to make.
This is very similar mechanical structures. For
Okay.
example, we have some bending structures could be there. We have a beam like structure, and beam could be bended in the middle or somewhat. It can be second thing can be like a circular structures or cantilever structures. So these kind of structures can your tool will be spotted or not?
See, I don't think that type of structure, but we are supporting optical illumination. If you want to make some laser or one minimum ionizing particle type of structures, you want to bombard that particle on your device and see what are the changes, that you can do in this tool.
Physics is totally involved in this structure, right? Thank you very
Yeah.
much.
Okay. Any question?
हाँ सर, एक क्वेश्चन मेरी तरफ से. मैं सिर्फ डॉक्टर फारूक हुसैन, MIT मुरादाबाद.
Okay.
बताइए, what is the difference between 2 gate and 3 gate, and what are the advantages of 3 gate technology over 2 gate technology?
Sorry, once again, can you repeat?
My question is, what is the advantage of 2 gate over 2 gate, 1 gate, and 3 gate over 2 gate?
See, this is the very actually what happens when we have a when you are designing your MOSFET at 180 nanometer. Okay, when you designing your MOSFET at 180 nanometer, then the distance between the source and the drain is very high. But when you are going some shorter dimensions, okay, then the distance between the source and the drain is very less. So the one effect is called DIBL occurring. DIBL is there. Okay, to suppress the DIBL, drain induced barrier lowering. Due to that DIBL, we are not having the control of gate over the channel. The control of gate over the channel reduces, so that at the zero gate biasing, at zero gate voltage, the channel is appearing and the conduction at zero gate voltage. So to reduce that type of effect, DIBL and other short channel effects, we have to introduce one more gate. Okay, so by having two gate, we are not having that DIBL effect and short channel effects. You can refer that one paper. I think one writer in that paper, he's showing that complete 6 leakage current that are occur in the bulk device, your conventional device with one gate only. So to reduce, he just propose if we are having 2 gates or we are having 3 gates, then we can reduce the gate current, gate leakage current, or your DIBL subthreshold slope. So that's why we are having more gates. Yes.
Try gate and 4 gate may be possible there.
Yeah, definitely. I already shown you that. I already shown you this structure. This is the 4 gate structure only. Yes. 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 एक minute. Just wait for 1 second. Yeah. See, this is the structure with the gate on all 4 sides. If you can see the gate, this is your gate electrode, and gate is on all 4 sides. If I remove this silicon, right. See, you can see. Can you see that gate is on all 4 sides? This is a triangular gate all around structure. Hello?
Thank you, sir. Thank
yes. Okay. Okay.
चैनल है ना, चैनल नहीं है क्या ये? It is around channel, I think.
Yeah, you can use, but you can for a 3D structure you require at least 4 GB RAM. Yeah. Processor is not very much importance, because for calculation we require RAM only. You have Core i3 dual core, that is not important, but minimum 4 GB RAM you require. No, actually it is not very heavy software. Actually I am having so many software in my laptop, that's why it is taking time. The software is only 390 MB. That is not very. Hello. Yeah, that's why. But if you are having 4 GB RAM, that is enough for doing a 3D simulation. But for CMOS inverter, it will take less than 10 minutes. Because CMOS is your, for 2D structure it will not take more than 10 minutes. For 3D structure it will take more than 1 hour and 2 hours for simulation. For some structure like I already shown you that trapezoidal FinFET, it will take around 6 and 7 hours for simulation. For yeah. So see, when you are fabricating your device, this is your actual virtual fabrication type of software. You are actually fabricating your device. If you are not giving your perfect information, then it will create some other type of device. That's why you have to follow ITRS. In the ITRS, you will get all the information. You will have all the junction depth information, doping information, channel length, everything. You have to follow that information only. No, this is good for MTech. See, if you don't know how electrons and holes are combining, how the ions are breaking, then how can you imagine, means how the current flows between source and drain, how the electric field is generating, where is the electric field, where is the effect of electric field. If you know, if you visualize, if you can imagine all those things, then you can, means you can do modeling, you can do device design, anything. So I think, yeah.
Hello, sir.
Hello. Yes.
Sir, I'm from Triple NUT Gorakhpur.
Okay.
Sir, I want to ask a question.
Okay.
Sir, in the from I love 180 nanometer MOSFET,
Okay.
there is a use of mesh sensor around the channel.
See, what I want to, I just want to, yeah,
I want to know
yeah,
why we have to use mesh sensor
okay,
and how to define its value according to my dimension.
okay, 1 minute. I just want to show you one thing. See, what is the mesh actually? Suppose this is your structure, okay? Now, you are having 4 points here. These are 4 points. The software will do all the calculation of these 4 points. But see, if your, suppose there is one electron here, then this electron can go here, here, anywhere it can go. So suppose you are having more number of points, then you will have the exact trajectory of that electron. But if you are having less number of points, then it will do some approximation. Suppose it will take this here, it will get the result. But now from here, the electron may move here, may move here, may move here. But when it reaches here, it will take this point only. So, but if you have the dense meshing, then you can have the exact trajectory of your current, exact trajectory of your electron and everything. Okay. So if you have dense meshing, you can have the exact results, accurate results. And now you are asking that how to define meshing according to your device size. See, basically what happens if you are having a channel length of 180 nanometer. Okay. This is your channel length of 180 nanometer. 180 nanometer is your channel length. Now you can define the 5 nanometer spacing. This is your 5 nanometer. 5 nanometer, so that your result will be approximate or near to the accurate only. Okay. Any other question?
Yes.
Yes.
Hello. 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 Am I audible?
Sorry, repeat once again.
Hello. Hello.
See, basically, I already told you the model is nothing, just a change in the parameter. If you are having some other material, see, already present model is there. But if you want to use any model which is not present in the tool, you can just change the existing value in the model. See, every material has some permittivity value, affinity value, some dielectric constant. You just change the parameter according to your requirement and you can make your own model. There is no need to have all the inbuilt models, you just can create your own model only. Okay. Any other?
Is there any other query from any other nodal center?
Yes.
Hello.
Yes.
I'm from VCSC Module in Jaipur. I want to know whether it is possible to visualize mobilization using the software.
Yeah, definitely. See, actually this is the Windows version and this is 5-year-old. In our Linux version, you can even see the strain, because some people are using strained silicon, so you can see the strain also in the silicon. What is the value of that strain? In that Linux version, you can see the mobility, and there are I think around 25 number of parameters you can see, like your power, your strain value, your Fermi potential, Fermi value, everything you can visualize.
IGDT Delhi. You have any query?
Yeah, definitely. So many people are working in IITs, NITs. So many people are working in the gate all around. I already shown you that when you create your structure, you just save it as a symbol, and then you can use that symbol in your circuit also. Yeah, definitely. See, if in that circuit if already is a MOS, you can replace that MOS with your gate all around structures. Yeah, you just have to use the mole fraction. You can use gallium indium arsenide, gallium indium phosphate. What kind of material you want to use, you just give the definition. You have to use mole fraction. So, repeat please. Yeah, you can use 3-gate material, 4-gate material. You want to use, see one more example I have. See, if you refer that Pankaj Pal paper here, he is using 2-gate dielectric materials. Okay, one high K, one is low K. So you can just define the in what region what type of material you want to use. You can use any number of material. There is no limitation.
One more question: can we see the skin effect using this software also?
What effect?
Skin effect.
Skin effect. I think that is from EMT, electromagnetic theory. I think. I'm not right now. I'm not confirmed with that skin effect. I will let you know.
Thank you so much.
Okay.
So, any other query from any other center?
Hello, very good afternoon, sir. I'm calling from JCRC. Can I ask you a
Yeah.
simple question that are you recording these sessions?
Yes, recording is going on. Yeah.
Okay, sir. Can you provide us with today's session? Because if someone wants to practice with this software, can you provide us the video for today's this session, afternoon session?
Yes, all the sessions will be available on YouTube. I think yesterday's.
Type VLSI, right? This date and NITTTRCHD.
Okay.
Day 1 or day by day.
Okay, you can type VLSI design program and date, and in that program you can type day 1 session, day 2 session. Accordingly, you will get the session of that particular day on YouTube, right? I think yesterday's sessions are already there on YouTube. Yesterday's sessions are already there on YouTube, so you can explore those sessions. If anyone missed any lecture, then you can view those lectures on YouTube. So if there is no more query, then I think we can close our today's sessions here only, and it is time to thank our engineer Gaurav from Cadre Design Systems, New Delhi, and he has given us a very good exposure of visual TCAD, where we can create our own device. You can create your own device by using different configurations. You can change the doping concentration. You can change so many parameters in your device, and then you can create your own transistor. You can save your transistor as schematic, as a symbol in your library, and then later on you can use that symbol or schematic for your larger designs like inverter, and you can make gates with the help of those schematics. So this overall session was really useful, and creating transistor itself is a very big task. So many different parameters are associated with single transistor. So many different you can say configurations are there. So lots of options are there in this software. You can explore all those options. You can create your own transistor. This is the only limitation with other softwares. You can't fabricate your transistors. You can fabricate your transistor here in Visual TCAD.
Yeah, you can see the virtual fabrication,
Yes.
and if you want to fabricate your device, then we are having a one company which is True Chips. We are collaborating that company that is actually Foundry. They can fabricate your device also.
Okay.
If you are confirming that your device will work perfectly fine, then we can provide you that fabricated chip.
The only thing with other softwares is your fabrication and how to virtually simulate your device. That part can be means done here, and later on if you are done with your chip, as he said, one
chips.
company is there, they are also making their chips, so you can explore these things and you can go ahead with your research in these areas also. So I'm really thankful to Mr. Gaurav from Cadre Design System for accepting our invitation and giving us this very good exposure of this visual TCAD, and I hope it will be really useful for all the participants at our nodal centers. And with this, we close our today's session here, and tomorrow again we will start at 9:30 in the morning. And tomorrow you will get exposure of Cadence software for VLSI design. Thank you very much.